Okay, hello people. Let me double check. Things seem to be fine. Can somebody write in chat with respect to the audio, like is the volume good? Can you see and hear? And if yes, then we can start. And if not, then we'd have to debug something. All right. Still waiting for... Let me just double check actually. Okay. Maybe I can turn the gain a little bit. Okay. So if there's any problems with the stream, please let me know. But otherwise we will start. I feel like I will have to give some amount of introduction. The last time we streamed this project was like almost 2 years ago, I think in January 23. A lot of time has passed since then. And ironically, I will glaze over some things that we covered in the last stream because ironically the stream today is going to be sort of a continuation of the stream from last time, despite the fact that there's been like a year and a half between them. But before that, so what are we doing today broadly? So we have this project that is exploring the beautiful world of Vulkan and geometry rendering and efficient dispatch and culling and stuff like this. And this project was originally written for NVIDIA hardware when NVIDIA shipped the mesh shader extensions. And on NVIDIA hardware, always things were fantastic and great. There's like mesh shaders and task shaders and culling and dispatch and like everything worked pretty well as far as I can tell. And we've always beaten the default rendering pipeline. So we have this demo where we are rendering a lot of geometry. This is not a wireframe view, but there is like a lot of triangles here. Right now we are rendering 50 million triangles in this view. I should mention I tweaked a bunch of stuff since last time around like level of detail following some mesh optimizer work that has happened. And so I think we are rendering fewer triangles now, but we are rendering the same quality of an output because the levels of detail are optimally selected. But anyway, so within this demo, the default mode is using task shaders and mesh shaders. And we can switch to the rasterization pipeline like the default one. And on NVIDIA, whenever you do this, the default is always slower. Now I'm using an RX 7900 GRE GPU. It's an AMD GPU. It's kind of 7900 XT, but like slightly lower power. I kind of like it. The problem is that our code doesn't work super well on AMD hardware. It kind of has never worked super well on AMD hardware, and then every new generation of the GPU that I tested on, I discover new problems and we fix them. So last time what happened is I got a 6700 XT card, like an AMD card, so the previous generation. And we have had significant bottlenecks and we fixed them, and this was a year and a half ago. Since then, I got a new GPU. It's a different AMD GPU. It's a next generation. Turns out it has new bottlenecks that we did not see before. And I'm not sure if it's because it was an older generation card or if this card is just faster. But I'm going to talk about kind of the problems that we see now. But so there's this demo. Right now, the state on AMD hardware is not great. We take 5 milliseconds, give or take, to render the scene. If we disable this beautiful task shaders and mesh shaders and stuff, we render the same thing in 4 milliseconds. So we are slower, despite the fact that we render more triangles in the default, in the like basic mode, I guess. So 53 million triangles, it's in the title bar, and then 47 million with the task shaders and mesh shaders, but we are slower. We also have a mode that does occlusion culling for individual meshlets, for individual clusters. And when we enable this mode, it's even worse. So I'm enabling this mode. We are now rendering 17 million triangles. This is because on a scene like this, the occlusion culling efficiency for an individual mesh is kind of not as good. You know, like what's the chance that a mesh is behind, like just not visible at all. But when you split it into meshlets, then there's a much higher probability that a given meshlet is just not visible. So it's way fewer triangles, but the frame time is like 9 milliseconds. So it's really bad. And the goal today, and again, none of this happens on NVIDIA hardware, and we're going to talk kind of about reasons and try to fix them today. Two caveats. This is a kitten, not a bunny. So two caveats. One is, it's been a while since I looked close at some of the details of this code base. So maybe I'm a little bit rusty, I'm not sure, we'll see. Two is, we are streaming from Linux. There's a reason why we are streaming from Linux. I mean, I use Linux day to day as my just daily driver, but there's a reason why we are streaming from Linux, which I'm gonna go into. But there's two things to know about Linux. First is OBS is not, for some reason I installed OBS like yesterday, I think, and tested it a little bit, and it's kind of fine, but occasionally there's some weird issues with this, so maybe there's going to be problems with that. The more significant problem is this. On Linux, there is no, on Windows, there is a feature called TDR, Timeout Driver Recovery or something, I forget. Essentially, if you manage to hang your GPU, then Windows like scheduling mechanisms will detect this, terminate the shader that is hanging your GPU, and kind of recover smoothly. On Linux, this does not exist. We are gonna be writing GPU, we are gonna be changing code that is heavily reliant on the GPU today. If we make a mistake, then what will happen is the GPU will hang. I think there's a mechanism that terminates, you can like kill the graphics like layer, graphics stack or something like this. But I think the upshot is maybe the stream will terminate if there's a bug and the bug hangs the GPU, but I will try to like recover without like restarting the stream, because hopefully that will work. Last time we had the same caveat and I think nothing went wrong, but again, it's been a year and a half. I don't really remember some of the details of this code, so who knows. So that is fun. So let's, something that we have not done before and something that will be valuable to do today is to look at the profiling results of the code that we are running using AMD profiling tools. But first, let me super quickly outline like the basic pipeline. I've also switched to Firefox since last time, and like some problems exist in Firefox that I'm not really used to. I haven't used Whiteboard in a while, so anyway. There's going to be some rough edges today, but hey, hopefully the content is still good. So let's look at the code. Let's look at rather the pipeline. So we have a lot of meshes that we're rendering, right? And it may seem like a straightforward task because you just throw a bunch of meshes on the GPU to process. But we are using mesh shading. So if we go to here, I think, then you will see that what actually is happening is that every mesh is split into these individual clusters, and this split is valuable for a few reasons, but one of the reasons is we can reject individual clusters before they even get to the GPU to process. You can see that the density far away is kind of like higher, but we have a level of detail enabled. This is a mesh level of detail. This is not like nanite type stuff yet. If I disable level of detail, then you will see that there is like way more. We are rendering 500 million or something triangles now, etc. It's like way slower, presumably. Yeah, it's like 20 milliseconds instead of like 5 milliseconds, etc. So, but this is kind of what we're working with, right? So every mesh is split, every mesh has a bunch of levels of detail. Every level of detail is split into meshlets. And then we pick the level of detail per mesh and then submit meshlets to the GPU. But before we do that, we do culling on a mesh and meshlet level. Now, normally you would think the way you would do this, like, I guess what we started with way back when, and the state before the last stream was as follows. For people who are not familiar with the project in general, the project is hosted on GitHub. It's open source, of course. It has all of the history. It has like 20 YouTube streams, and this will be the 21st one that went into developing this. Most of the project has been developed on the stream, so if you are not sure why a particular part of the code is like this, you look at kind of when it was done through the Git history, and then go to the YouTube stream, and then I will probably talk about why in that YouTube stream. But in the last year and a half, I've submitted a little bit of stuff to this project. Nothing like super substantial, but again, some things around level of detail, some cleanups and stuff like that. All right, so of course the stream will be on YouTube after the stream finishes, so if you don't have time to watch it and just came to say hi, then that's perfectly fine, and you can watch later. You can watch it like 3 times the speed or whatever. So normally the way you would write this pipeline, and what we started with and what we used to up until the last stream, is like this. You have a bunch of draw calls. Okay. And then every draw call has like position, mesh ID, and stuff like this. Then you go through the culling phase where for every individual object, for every individual mesh, you check if it's visible. And then you pick the level of detail. And then this is kind of the object that you have to render, right? And then you have the array of these draw commands. And then for every draw command, you submit the draw call using task shaders and mesh shaders. Task shaders are used to process sort of the draw calling works at the granularity of a mesh. The mesh shader works at the granularity of a meshlet, or rather like a triangle. It's kind of hard to, let's just say a meshlet. But for a mesh shader, what happens is you have a meshlet and you have like 64 threads on the GPU, and they cooperate to produce triangle data to pass to the rasterizer. What we want is we want a stage between these two that can work on the meshlet level, that can cull individual meshlets if they're invisible. But we don't want to do this in the mesh shader, even though we could, because in the mesh shader we kind of are already rendering the meshlet, and we could use 64 threads to like collaborate on deciding that this instance of a meshlet is not visible, and then submit 0 triangles to the rasterizer, but that's generally not super efficient. So when NVIDIA came out with these extensions, they introduced the task shader stage. In Direct3D 12, this is called the amplification stage, although it doesn't have to amplify the amount of triangles or whatever, it can also reduce it. And so then what happens is you have each task shader thread is responsible for culling meshlets. Okay? So we have an array of draw calls, and then each draw call submits a bunch of task shader threads, and then each task shader thread is responsible for calling one meshlet. And then if it's visible, it outputs like an invocation for a mesh shader work group, and then that is what renders triangles. Cool. Now, the problem that we had last time is, and then just very quickly we need to talk about occlusion culling. because it's kind of important. It's not critical to the it's not like it's not the only reason why we are having the problems that we're having with efficiency, but it's part of the reason. So in addition, when I say culling, what do I mean? Of course, we do frustum culling. We do frustum culling for the meshes, and then we also do frustum. Do we? I think we also might be doing frustum culling for the meshlets. I don't recall. As I said, it's been a while. Maybe we don't. Oh no, we do, yeah. So we do frustum culling for the meshlets. This is a little useful. For example, so if I run this again, you see this kitten in the bottom right. Obviously, the mesh extents are kind of large. There is like a bunch of meshlets that are outside of the frustum range, outside of the like window. And normally what happens is the GPU processes triangles and rejects them. But when we work on this meshlet granularity, we can also do frustum culling for it. And it's very cheap, so it's like worth doing. It may not be super worth doing, like it's not a giant deal, but it's kind of nice occasionally. So then we also do backface culling for meshlets. I've talked about all of this in the past streams, so I will not repeat this. But the most important thing that we can do now is occlusion culling for meshlets, but we also do occlusion culling for meshes. So how does occlusion culling work? This is a complicated area where there's a lot of different possible solutions. The solution that we came up with, or we didn't come up with it, solutions that we are using is the two-pass occlusion culling method that is based on the hierarchical Z buffer. It is fairly widely used at this point. It is used by Unreal for nanite pipeline. It is used by Alan Wake in their geometry pipeline. And it has been originally proposed in like 2016 or so. So it's been a while. This method really relies, or to the extent that your pipeline is GPU driven, like this method is easier to implement and can be more efficient. So this is part of why we are doing full GPU pipeline. How does this work? You have two passes. We are calling them early and late. In both of these passes, we are potentially rendering geometry on screen. In the early pass, we are rendering geometry that was visible last time. So last visible. This is potentially a subset of the full amount of geometry. For example, if you turn the camera a little bit, what was visible last time is some amount of objects on screen, and then some objects went out of view, and then some objects came into view. So we're rendering only the last visible objects, and then this renders depth data in addition to the color data, and then we are doing a hierarchical Z pass, which is building a pyramid of the depth data. And I had visualization for this. Let me try to think. If I press P, it's kind of hard to see, but you see a faint outline of like a mesh in the bottom right corner. And then I think if I switch, oh yeah. So we take the depth buffer and then we progressively downsample it so that at every resolution we have a version of it. And then we can use this to do occlusion culling for basically anything. And the results of this occlusion culling are conservative in the sense that if the object, we like rendered some objects on screen, so if something is behind the objects that we have just rendered, then it's kind of not visible, right? So then what we do in the late pass is we render objects that were not visible in the last frame. And when we do this, we do occlusion tests. And we also do, there's also like a pass that does occlusion tests for objects that are visible to record it for the next frame, because if you don't do this, then objects will kind of be always rendered in the early pass. Anyway, I go into all of this in some of the earlier streams, but the point is we submit geometry twice. And then for every individual object or cluster or meshlet, it's either rendered in the first pass or in the second pass, or it's not rendered at all if it's like not visible. What happens when you have stable camera and stable scene? which is our use case, is after like one frame when things are computed. And I should say the scheme relies on temporal coherence. The scheme relies on if an object was visible in the last frame, it's likely that it's still visible. Because of this, if we render them in this early pass, the early pass, on one hand, you don't render too much because you're just rendering what was visible last time. On the other hand, you hopefully are rendering enough for the hierarchical Z buffer to be kind of a good enough occlusion, good enough for occlusion. This scheme never renders, it doesn't have disocclusion bugs in the sense that you never have a case where an object should be rendered, but it's not. Compared to this, early Unreal titles in Unreal 4 era used a different scheme where, and I'm pretty sure, I guess I don't know if Unreal 5 still has this code, I'm guessing yes. So there's a different scheme that was popular in the industry where you do kind of a similar thing, but you only do a single pass, and you use the last frame's visibility information as well. But if the last frame's visibility information is incorrect, then you just have visible gaps. In Unreal 4 titles, you can often see you turn a corner and there's like a white flash, or sometimes whatever the background color is, like the geometry is not visible and then it appears next frame, and you see this briefly. This scheme doesn't have this problem. It may render objects that are invisible in the sense that it's not perfect color, but it can never render objects that are visible. It can never skip rendering objects that are visible. Anyway, so why is all of this a problem? When you do all of this on an individual mesh level, then what happens is we have a compute culling shader here and here. That works on a level of individual meshes and then produces kind of the command lists for these early and late passes. And when you don't have clusters to worry about, and I should say the code supports occlusion culling on a mesh level, regardless of whether you use mesh shaders or not. It's like an important efficiency thing that's unrelated to the task shading and mesh shading. So when this culling stage, in the stable frame situation, this culling stage works on individual meshes, and so after the first frame, it should produce no meshes to render for the late pass. In fact, if you look at when we run the code, we have these two counters in the title bar: render and render late. Render is this early stage and render late is this late stage. And you can see that, and also we do culling, cull, and cull late. You can see that culling is super fast. Cull late is slower, but like decently fast. Maybe it could be faster, I'm not sure. And then render late is super fast. The reason for why render late is super fast here is in this mode we don't have occlusion culling for individual meshlets enabled. So the culling stage produces 0 objects to render for the late pass. In this case, if the camera moved or if objects moved, then you would see some amount of objects rendered in the late pass, but it would be small, hopefully. And then the reason why cull late is kind of slower than cull is cull doesn't do occlusion culling, it just does frustum culling and stuff like this. And then cull late is the phase that does occlusion culling for current and previous objects, and so it's like more work to do, so it's a little bit slower. It's fine. Now, if I enable occlusion culling for meshlets, you will not see this on screen, which should make sense because the only objects that would not be rendered are the objects that are invisible, so you can't see them. We could enable wireframe mode. I don't have this code, but if you had wireframe, you would see kind of objects appear and disappear. Actually, we could enable. Maybe you can. Does it just work if I? Yeah, I think we'll try to run this with wireframe now. But the problem though is, as you see, when we enable occlusion culling, the early render is still kind of the same 4.5 milliseconds or whatever it was, and the late one is 4.4 as well. So what we are hoping for is that the second pass in this case is very fast, but actually it's really slow as rendering the geometry. Why is this the case? Well, the problem is here that when you want to do occlusion culling, so remember this late pass, the culling for the late pass does like occlusion tests. And so when you do culling of individual meshlets, you need to do occlusion tests for these meshlets. And we do this in the late pass using the task shader that NVIDIA taught us to use. And unfortunately, using the task shader, as it turns out, using it at all, but especially using it in the mode where the task shader does a bunch of work to reject clusters or meshlets, and then does not produce useful geometry in the end, is slow on AMD hardware. And there's two ways. If you want a lot of details about some of the internals, there's this open issue on the repository where we are discussing this with the developer of RADV. My sense is this happens, by the way, on both the Linux and Windows drivers. My sense is that the issue is kind of endemic to the hardware implementation, to the hardware support for task shaders or lack thereof. But there is like a way to improve the situation, which we will do now by patching the driver. But that's kind of, you can't patch the driver on Windows. And then it's not clear if patching the driver actually results in optimal performance or if it's just making the problem less bad. So to understand this problem, we're going to have to look at the capture of the situation with like occlusion tests, which we're going to do now. All right, cool. Well, they want more bitrate. I'm not giving them more bitrate. Okay. So why are we streaming from Linux? The beautiful thing about Linux is that Linux has open source drivers for AMD hardware that you can just build and use. So right now we are using RADV driver because that's what's installed by default, but this is the build from, I guess like from Ubuntu package manager or whatever. Like I didn't build it myself, but we have a repository checked out here, which contains the source code for RADV. You can build the user mode driver yourself. The build is super fast. It's just a bunch of C, sometimes maybe C++ code. And I already have it checked out and built. The build setup takes like a little bit of work, but I think it took me, I did this like last week or 2 weeks ago, and after not doing this for like a couple of years, and I think it took me like 15 minutes start to finish just configuring stuff and like installing packages and whatnot. But I already have it done. So the way this works is, let me increase the font size just in case. So I can just run Ninja here and Ninja will do something. We can do a clean build. I think it takes like 20 seconds or so, I forget. But if I do a parallel build, maybe video encoder will be, anyway, let's just look at the source code and let's just change something in some file. Let's take the header file for, so I just did an op change and then I'm just running Ninja and then it's building like a bunch of files. And then it's done almost. I changed the header file to like, to just build more than one source file. What the code that we actually need to change is in just one. But so it builds an SO, it builds a driver as a shared object. By default, when you run the code, it would still run the Vulkan code. It would still use the default driver available in the system. But there's this environment variable that I can never remember. So let me, So let me kill this for now. And then, wait, hold on. This is complicated. Okay. So if you point this wiki driver files environment variable, this is probably invisible because, hold on. Okay. Stream layout issues. So if you use wiki driver files environment variable to point to the like local build, then it picks up the driver that you have just built. Why should you trust me? Because there is no difference, right? Let's go into this thing, which we will have to use. And then let's just printf a bunch of stuff. And so we just changed some driver code. Let's run Ninja again. It builds the driver. This time the build is very fast, even the linking is very fast. I think there's like, the linking is fast, but there's one source file in RAD for some reason it's like slow to build. Anyway, so we ran the code again, and now we see a bunch of numbers printed twice that we just added a printf for in the driver. And of course, if you wanted to, you could debug the driver by just attaching the debugger and just stepping through the code and stuff like this. The caveat is the driver is open source, but this doesn't give you like all of the information about the hardware behavior necessarily. And the driver talks to this piece of hardware called firmware. It's not a piece of hardware, but like there's a magical piece of software called firmware that's like uploaded to the GPU and runs there somewhere. And you don't have the source for this and you don't fully know what it does. And it's a problem because this is part of the issue that we're having. But anyway, so the other thing that RADF can do, and this is what you could also do without RADF, with just like the MD driver, is to do a capture using a Radeon graphics profiler. So the way you do this is you enable RGB trace. It should print trace support is enabled. Let's disable actually the debugging thing. Okay. So, and then you can say, there's some way to hook up the hotkey capture, but it doesn't work on Wayland. Anyway, Linux is fun. But I think is this? One moment. No, hold on. Massive key trace frame. Okay, wait. So you can specify like which frame, the frame with which number you want to capture. This is not great for like a real application, but for us it's just fine. There is a way to, again, like if you use X, then I think the capture hotkey is just F1 and it'll just work. I think for me it doesn't work because there's some issues with the build. Anyway. So you can run it with this magical command. It will wait until the frame number 100, and then it will do a capture, hopefully. And then it printed this capture saved to. And this is a file that you can then open in the official AMD tool and look at the profiler. Oh, let me check. All right. So, all right. This is actually good. Okay. So this is what our frame looks like when we do not have this meshlet occlusion culling. Because I didn't enable it. Let me capture another trace with occlusion culling enabled, because I think it's going to be easier to explain what the difference is. I should say, if you use these tools a lot, you should instrument your code with VKX debug marker extension. But our frame structure is so simple that it's kind of just visually obvious as to where things are. So I didn't bother to do that. Okay, so let me switch it just by default to true, so that we don't have to like think about this. So we run the code, the occlusion culling is enabled, there's a capture that happens, it captured the thing, then you look at the trace. So let's open the second trace. If you use Windows, then Radeon GPU Profiler should work on Windows, and there you don't have to do this like driver environment variable stuff, you can just, there's a GUI to like do a capture. It might even work on, I don't have official AMD drivers set up on Linux because this is the newest Ubuntu and they didn't have binaries for this. But anyway, okay. So remember our problem. We have this early stage and the late stage of rendering. The late stage in our setup does culling on meshlets, but doesn't render anything because there is nothing to render, because every meshlet that has been visible has been already rendered by the first pass because our frame is static. Here's the performance profile that we see. We have, and I showed you in the title bar there was like 5 milliseconds and 4.5 milliseconds. This is the same data. So we have our frame. There is this first stage that renders geometry, and it's taking 4.8 milliseconds here. And there is the second one that doesn't render geometry, and it's taking like 4.5. There's a stage in between. This is the thing, I think there is the culling here, and also this is the depth pyramid generation, like this high Z pass. The way you know is because there's multiple events here. And then there's this culling thing that does occlusion tests. And there's the culling thing here. And again, remember I said the culling in the first pass is very quick, the culling in the second pass is slower, etc. Okay. Now we have a problem. Oh, and like what colors? What do these colors mean? So the cyan, I guess, or whatever, sky blue color means graphics work. And in our case, you can click on it, and it shows us draw calls. Which essentially means mesh shader invocations in our case. The blue thing means compute queue. And also, on Windows, the display is a little bit better because it shows this a little bit more correctly. Oh no, this is, never mind, this is all correct. Okay, never mind, all good. Okay, yeah. Anyway, so we have a problem. The problem that we have is what happens in the second pass. Like, why is it so slow? It looks as if it's doing nothing. It's submitting no work to the graphics queue, but it's taking a lot of time. What is it doing? To understand this, we have to unfortunately understand a little bit about how the task shaders are implemented on AMD. In general, I should say, so task shaders and mesh shaders are an NVIDIA invention, I guess, right? Like they published the spec originally, and now it's part of the sort of cross-vendor extension. AMD hardware had, for a while, something that sort of resembled mesh shaders, but didn't have something that resembled task shaders. My understanding is NVIDIA hardware is also kind of weird in how they like they don't actually have a task shader unit, but like we are not talking about NVIDIA hardware right now. So on RDNA 3, they have made improvements in the GPU architecture to make mesh shaders better. This is kind of visible in some of the performance results that you may observe on this code even. But they didn't do anything to change task shaders. So how do task shaders work? Let's look at the first pass, because this is the pass that actually does work, so it's kind of more interesting. So remember I said the yellow is the compute and the sky blue or whatever is the graphics. This is not, I didn't mean compute work as in compute shader, or I kind of did mean that, but I also meant compute queue. So actually, and our code doesn't use any queues other than the graphics queue. But what happens is the driver behind the scenes takes our task shader and runs it asynchronously on the async compute queue. So this is kind of that. As this task shader is running, it is producing work for the mesh shader stage. If you look at the shader code, then at the very end, there's this emit mesh tasks ext, which is kind of saying, hey, I generated a bunch of work, now run mesh shaders with that work. The driver translates this into writing out a draw command to a buffer. Let me. So there is this async, and remember, we didn't write this code, like the driver does this behind our back. So there's this async compute queue that is running our task shader that is actually just a compute shader. And every time our task shader invocation, our task shader or the work group finishes, it produces several meshlets to render. The way it works for us is we have interesting. Okay. I just thought of something slightly strange. Is this just okay? I don't recall. It doesn't matter. So the way this works for us is we have this config file where we say task shader has 64 threads and every thread generates 1 meshlet or 0 meshlets. So then the task shader invocations produces between 0 and 64 meshlets to actually rasterize. And then this compute stage writes a command, a draw command, that has between 0 and 64 meshlets in our case. And then each meshlet, I think right now I set it to like 96 triangles up to. And so grand total, you could have the task shader produce like 6,000 roughly triangles, or 0, or some number in between, depending on maybe some things are visible, maybe some things are invisible, maybe some meshlets have fewer triangles, like who knows, right? Some number of triangles between 0 and 6,000-ish. And that actually goes into a queue with like a hardware-specific structure for every piece. And that then runs the mesh shader. And that produces triangles. Okay. Now, this is interesting because these are two parallel processes. If you look here, what actually happens here is there's some geometry work that's been done, and there's some async compute work that's been done. And whenever there is kind of the geometry work needs the compute work to finish before it starts, in a sense, but it's not the case that you first run the task shader, produce a giant buffer of all the draw commands, and then draw from it. Because if this were the case, you would see kind of two bars that were sequential in the timeline. This is time goes left to right, right? So you would see a first stage and then the second stage. Instead, what happens here is the processing is overlapped. As the async compute queue is generating new draw commands, they are being processed. And if you look at these individual items, if you look at this top right corner where like the kind of information about them is shown, you can see it says VKCMD draw. One, I think, is a bug, like it shouldn't be 1. I think it should be a different number, maybe, or maybe I'm wrong. It doesn't really matter. We never use this command, right? Like this is part of the traditional rasterization pipeline, which we are not using right now at all. But the driver kind of translates this into the scheme where there's a command buffer that the GPU constantly pulls draw commands from. Okay, how big is this buffer, you might ask? Well, the answer is it has 1024 entries on RDNA 3 GPUs on both RAD and the official MT driver. How do I know? Well, I looked at the source code. You can look at the source code of the official MT driver, by the way, as well. It's just open source on GitHub. It's just harder to build. So I will not bother. And if you look here at what we were printing these number. At some point I looked at the driver source and found the place where this stuff is configured. So this means that there's a buffer with just 1024 entries. And then for every entry you have the draw command this is what this drawing bytes means. It's like 16 bytes per entry. And then you have payload that's much larger, that's 16 kilobytes. And what this payload is storing is the, where is this for me? It's this thing. It is this struct that, again, is part of the extension where the task shader can write a payload that the mesh shader will then have access to. And this is how we communicate what to draw. Why is this 16 megabytes? Well, it's 16 kilobytes per item. Why is it 16 kilobytes per item? It's because it's the maximum allowed by the specification. Curiously, if you look at NVIDIA documentation, it will tell you, hey, you should try to minimize the payload size because the smaller it is, the better hardware parallelism is going to be. We are actually being slightly wasteful here. We're using like 32-bit indices for Meshlets, despite the fact that it could be packed into like 8 bits easily. We just didn't bother. Maybe it helps on NVIDIA, I'm not sure. But on AMD, it doesn't even matter because they allocate, again, I think both drivers, RAD and AMD VLK, allocate 16K per task sort of workload, per task work group, and just call it done. So reducing this shouldn't even matter for performance on AMD hardware because this is not what the bottleneck is. Okay, so 1024 draw calls. And remember, I said one draw call for us is between 0 and 6,000 triangles. So in total, even if you use the maximum amount of triangles for each sort of item, 1024 is only enough for 6 million triangles. But we are rendering like 50, 60 million triangles, like however, much more. How does this even work? Well, the way this works is instead of the buffer being filled start to end and then the kind of other stage picking this up, the driver or the buffer is a ring buffer that's being reused. So what happens is you have the sync stage fill an element. And then it marks it as like you can use it now. And then there's some other part of the GPU, which is called command processor. And it's part of this magical firmware thing that we don't have source for, so we don't fully know how it works. But there's a concept of a ring buffer there where it has a buffer and says, cool, this item is now ready, I can pick it up, it has a draw command, I will draw it. And then I will free this item for subsequent work. And so the async compute task, instead of just filling the buffer, it fills every entry multiple times as they become available for recycling. The specifics of this are not part of the source code because it's kind of how the GPU works. I don't know to what extent it's documented. I haven't checked. But the one thing we know is 1024 entries. So why is 1024 entries bad? Well, in theory, the problem is like this. Let's say that what you want is you want this culling stage and this geometry processing stage to run kind of in parallel. And if you have a large ring buffer, then what happens is you fill a bunch of entries in the ring buffer, and then for the stage that's consuming this ring buffer, there's always a lot of work to do. And so you're rarely waiting on the other stage until you fill the entire ring buffer. What happens for us, though, is what seems to happen, and because it's all part of firmware, it's not super documented and has no source code, I don't know exactly why we observe the performance that we do here. It's a little bit weird, but what seems to happen essentially that the buffer is so small that the two stages always fight for kind of entries in this buffer, and because of this, the efficiency of every stage is actually super low. You can look at the efficiency. In GPU, there's this concept called occupancy, which we will not go into, but it's like the higher the better. And you can actually see these bars. The bars from the middle to like the top are graphics work. or graphics queue. From the middle to the bottom, it's async queue. You can see that when we do culling, for example, we are really well filling the graphics queue. It's like good. But when we have this async thing starting, it runs a little bit, and then presumably it runs into this bottleneck of like it went up until the end of the queue, so it finished writing 1024 items. And now there is something for the GPU to render. So you see these small green things at the top. This is like the GPU is picking up a little bit of work to render, but there's not that much. And then because these entries are being used by the rasterization work, the async compute work can't really proceed because it's like written all of the data that it has space for in the buffer. So it has to wait for space in the buffer. And presumably, there's also not enough work in this buffer to fill the geometry pipe like well. So everything is bad here. To add an insult to injury, when we have no triangles to process, you would think like you can't be bottlenecked by the geometry stage, so it should be instant. But the problem is, if you look here, I think if you select these, maybe, let me try. Oh my God, you can't even. So if you click on these, this says VKCMD dispatch with 0. Again, so RGB trace here is not super accurate because it's all kind of, I think they're repurposing. Anyway, it's not necessarily exactly what's happening, but what seems to be happening is that you still have this very short queue. The task shader stage is doing this culling. It has no geometry to render, so it just writes empty commands into this queue. But the queue is still there. It is still the case that you have a 1024 item queue, and even if there is 0 meshlets to render, there still has to be a command that's written into the queue. Then the firmware command processor picks up this command, says, oh, 0, I don't need to do anything, and then marks this command as being available for reuse later. And so you're limiting the efficiency of the stage that's producing these commands, even though you never produce any actual work. So with that very long preamble, so like how do we kind of prove to ourselves that this is even like remotely accurate, as in maybe all that I'm telling you right now, because I'm not an AMD engineer, I don't have secret GPU documentation, who knows how it actually works. Maybe all of this is not true. Well, let's try to validate this hypothesis by having more entries in the queue. Why are there just 1024 entries in the queue? I'm not sure what the actual hardware limit is. It seems to be fairly large, but we are allocating this worst case payload size for every entry, which is bad. Ideally, it wouldn't do this. There is problems with fixing this. You can read the GitHub thread to understand these problems. But it's just memory. We have a GPU with a bunch of memory. It's fine. I think this might even be CPU memory. I don't recall. So if we wanted to make the queue like 10 times larger, it would be 160 megabytes of payload ring instead of 16. Is it good? No. But can we test performance in this configuration? Definitely yes. So what you can do is you can just patch the driver. So I had this patch. Is this thing called anywhere else? No. This function is called like once when the driver starts up the device. It's not performance sensitive. So I had this code here that I'll just rewrite, which is, let's just get an environment variable, and then if it's there, then sort of reassign. So basically just allow us to test the behavior with a value that's different from 1024. You could just hard code a different value, but then you'd have to rebuild the driver all the time. That's not fun. So just patch it, and then we'll see different numbers being printed here. All right, so let me go back, and I should say all of this so far I just have done of stream, so this is nothing new, but the new parts are going to be changing our code to not hit this problem, which we're going to start doing shortly. So build the driver, and then if we just run this again, I have to disable tracing. I don't want to spend too much more time on this. I'll disable tracing. There's a reason why I'm doing this, but like read the thread. So if I just run it again, it's the same. It's like 9.3 milliseconds full frame, and the first and the second pass are kind of slow. Now we have this environment variable. Oh, you can't see this because, okay. So now we have this rad task n that we can override. This value is baked into the shader microcode. Cache will break if we don't disable it. Our GPU will crash and the stream will burn. So we have to do this. And I hope I typed it right, because I didn't, then our stream will actually crash if we change it. Okay, so let's try to increase this a little bit. Let's try to go to 496. So we can see now that the total frame time is 8.5 milliseconds instead of 9.5. And the times are a little bit smaller. So increasing the queue, and we can see that the number has been actually applied. We are using like 60 megabytes for the payload buffer, etc. So the value is working. In my earlier tests, I've empirically discovered that the maximum reasonable value for this specific application is 32K. If you do 32K, then you will see that the early pass is 1.5 milliseconds. Remember, it was 5 milliseconds before. So more than 3 times faster early pass. And also the late pass is 0.4 and it was like 4 something. So 10 times faster on the late pass. So if these were the performance numbers that I was just getting out of the driver, then the stream wouldn't have even happened. Because it's like good performance, we can disable Meshlet pipeline. We'll see higher frame time, we'll see much more time spent on rendering, etc. So these are the numbers that I expected. And in fact, I think on 6700, like I was seeing reasonable results. Modulo some stuff that happened on the previous stream, which you should rewatch. But the problem is that we had to patch our driver to actually get here. Now, oh, and like if this was, so let's talk about the problems. The good news is that the performance is pretty good. The bad news is we are spending 530 megabytes on the payload buffer. We aren't actually using it because our payload use is like a few hundred bytes out of the 16K maximum. But the driver allocates 1-to-1. It allocates 1 draw command, max payload. Fixing that is complicated. And which is to say, I can't just submit like changing from 1024 to 32K to Mesa as a pull request, because that would mean that the driver uses 500 more megabytes of memory, and that's like a problem. You should not be doing that, right? So ideally we would stay within the same size, but the 16K limit is allowed by the spec. So you have to have somehow this allocation be dynamic, as in if my task shader is using like a few hundred bytes, I should get more entries in the queue. There's problems maybe with doing that. It's not clear. One of the RAD devs who made the original like implementation hopefully is going to look into this. The second problem is the official AMD driver is kind of open source as well, but it's separate code base. I'm not sure what restrictions, like maybe it's the exact same solution that could improve both, maybe not, I'm not sure. It's complicated, right? And then of course, if you are shipping a game today, and let's even say you're using mesh shaders, like you're shipping Alan Wake 2. If you read, so Alan Wake 2 had a great talk on Digital Dragons last week or 2 weeks ago, whenever that happened. There's a video on YouTube that you can watch, that you should watch. They go into some of the culling stuff that they do. They do the cluster culling, cluster occlusion culling. They do this in the mesh shader, which at least they said they do this in, why don't they do this in, anyway, they do this in the mesh shader, but I think they might have tried, I'm not sure if they tried task shaders, but if you were shipping a game like this and you would try to use task shaders on today's production AMD drivers, you would see bad performance, and like it's not clear what recourse you have, right? So that's one problem. there is some other subtle stuff around this. And the other big thing to know is, so if I run this with 16K instead of 32K, oops. Now the full frame time is 4.6 instead of like 2 point something. Everything is slower, render rate is way slower now. So it's not even clear. For some reason at 32K we are seeing like fairly good performance. At 16K we're seeing fairly bad performance. It's not clear why the jump is this dramatic, and it could be that we aren't even seeing the best performance right now with this driver patch. Like it could be that the GPU can do better, but for some reason this mechanism is still limiting something. So that's not great. So there's a bunch of issues associated with kind of trying to fix the driver for this, right? Now, I believe that the drivers need to be fixed. I believe that the task shaders essentially are not really usable from the performance perspective on AMD hardware right now in either driver. I should say, I discussed this problem with somebody who had a D312 implementation of something reasonably close, and they saw the exact same behavior on D312. So basically, it's just a problem of AMD drivers / hardware / firmware, right? I think it should be fixed. Whether AMD people will want to fix this or not, I don't know. But while the problem exists, our code is like in a bad shape, right? It's slower than it should be. And the other thing to note is, so let me disable cluster culling. Okay, so once I disable it, we are seeing 3.5 milliseconds of render time, and we were seeing like 5 before. So even when you don't do occlusion culling on clusters, when you don't have the second pass that's super inefficient, there's still efficiency loss in the first pass. So like the problem is there regardless of how much you cull. It's just if you use task shaders, you're potentially hitting this bottleneck. It's probably dependent on how much geometry you have, what GPU you have, etc., etc., etc. But like the bottleneck is there. So what do we do? Well, this all kind of sucks because task shaders provide a very convenient way for us to not have to manually manage kind of this situation ourselves. But we can manually manage the situation ourselves. And so we will try to write some code that fixes this problem by essentially removing the use of the task shader. And instead of the task shader, we will gonna repeat the work that the task shader is doing in compute. But instead of doing the thing that the driver is doing, which is like the whole async compute with synchronization and stuff, which we can't even do because Vulkan doesn't expose any legal way for you to run kind of two shaders concurrently in this way. Anyway, like you can't re-implement what the driver is doing and you don't want to. But what I want to do is I want to just run a compute shader that generates the list of visible clusters. And then just run the mesh shader that will read from the list of visible clusters and render them. The only caveat is that it's going to be a lot of memory. But, you know, you have to do what you have to do. Because of this, it's likely going to be less efficient on NVIDIA hardware. I'm not sure how much less efficient, but, you know, like there's just not a lot of great options. It kind of required here. And my understanding is that, well, no, anyway. So we're going to try to do this in a fairly naive way. We just do this work in compute where we produce a list of clusters. And then if it works, maybe we'll think about reducing the amount of memory, but we spent like an hour doing the exposition and the profiling and all of this, so probably we will not really have time for this. Let me do one last run with this patch driver, and then I will undo the patch to not like mess up accidentally with some environment variable stuff. But I wanted to capture, hold on. So let me go back here and I will disable caching and do 32K. And I will enable RGB, which is not great. But I just want to show. So the other problem with all of this is that when you have tracing for the profiler enabled, it actually skews the numbers in this case by a lot. And so the trace that I'm going to show you is not actually the real thing that happens on the GPU, but it's kind of, so here's kind of the picture with 32K buffer size. Again, it's not quite correct because of reasons like there's this giant gap here, which is essentially the profiler is capturing the information, which doesn't actually take time if you aren't capturing the profile. But you can see that once the queue is fairly large, then this stage, the culling stage, takes little time, like 0.13 milliseconds or whatever. And it produces no rasterization work, so there is nothing more to do, right? So this is kind of the world that we want to be in. Yes, we will spend some amount of time culling these clusters, like it's unavoidable, it has to happen. But once we do that, we don't expect there to be any more work. And while we are doing this, like remember it's kind of hard to show well here, but in the previous capture, a lot of the work, oh, actually, yeah, you can kind of see this here. So in the original captures that we're looking at, the efficiency was really low everywhere, including the geometry stage. And here, at least, the efficiency for the geometry stage is a little bit better than it used to be. And then anyway, so we want a profile that kind of looks more like this section. Ideally, it would look more like this section for the entirety of this render. I don't know, because enabling tracing slows things down, it's kind of hard to correctly validate all of this, but here's kind of the world that we are in right now. So let me disable, so let me just undo all of the driver stuff. I can do this by, so I'll kill this, wait, okay. And we are gonna switch, we don't need the custom driver anymore. So I think we're just gonna, and we don't really need mesa sources anymore. So let me switch back to just the regular driver. Okay. So this is kind of what we are doing today. So I'm sorry the introduction was so long, but I think it's the oh, okay, cool. Thank you for clarification. So Alan Wake 2 does do meshlet culling in CS+. And so okay, so Alan Wake 2 is basically doing what we're gonna do today, more or less. So that's cool. And no other questions, so that is good. So here's the reason why, I mean, part of the reason why I didn't do this full cluster thing. Let me, okay. Part of the reason why, oh right, so the editor is Z-E-D. It's I've been using it full time for the last like 4 months. It's, how do I put this? I don't love it. I like it, but I don't love it. There's a bunch of stuff that they don't do right. Some of the stuff, if there is, it's like open source, you can fix some things easily. It's written in Rust. Some things are difficult to fix because you have an unfamiliar code base where something in your workflow doesn't work well, and like, how do you, where is the code that does this is unclear. There's some stuff that is just philosophically different. For example, Z heavily relies on format on save. Format on save is interesting in C++ code bases that usually aren't formatted, and a lot of the time that I've spent getting comfortable in Z is like tweaking various things in various places to like have things line up. But overall, I like it. It kind of replaced Sublime and VS Code for me. I don't like VS Code and I like Sublime, but Sublime was becoming kind of not good enough. And so Z for now is for me the good enough editor. All right, so here's the problem. Here's the only reason why kind of I didn't even like why the first time where we are writing this code is going to be like right now. So I will omit some details because again a bunch of the stuff was covered in the last stream, but the way our pipeline works right now is, yeah, so we have this limit of 4 million work groups because of the issues with the previous generation of our MD. We had to switch from this naive pipeline where you have draw calls that dispatch tasks, that dispatch meshlets, to a single draw call. For example, on NVIDIA GPU, as far as the GPU is concerned, you will have one draw call because they don't do this weird like command processor async stuff, as far as I know. So you'll have just one draw call. And then this one draw call has a bunch of meshlets or a bunch of task kind of groups. And every task group has up to 64 meshlets, and it kind of renders them. And the reason why we did this is because on RDNA 2, we hit the same limit kind of that I was just explaining, but we hit this in the earlier stage of the pipeline where the draw calls are submitted to the GPU. Because we'd have a bunch of empty draw calls or a bunch of draw calls. I guess it was kind of similar, like there were a bunch of draw calls with... Anyway, I don't want to belabor this too much. I want to start writing code, but the upshot of this is we kind of migrated to the system where the calling stage doesn't output the meshes that it needs to draw. It outputs the sets of 64 meshlets that it needs to draw, which we are calling tasks here. And then they correspond to task shader invocations. This is actually convenient because it's going to make it much easier for us to rework the code to do full compute cluster calling. In a sense, you can think of the previous stream that happened a year and a half ago as preparation for this stream. The only downside is this. So my plan right now is to write a compute shader that calls tasks like this, like meshlets and stuff like this, and just writes a buffer of cluster indices. How big should be this buffer? Should this buffer be? Well, it's however many visible clusters you have. How much is that? Well, it's complicated. Like if you have occlusion calling working well, then it's not a lot. But in the first frame of the application where there is no prior visibility data, occlusion calling doesn't work at all, because there is no historical data, so you can't like fill a Z buffer with anything meaningful. So in the first frame, you actually are rendering like a lot more triangles than you're rendering on subsequent frames. What if you disable level of detail? What if level of detail doesn't work as well? What if you increase the draw distance? Like, it's just what is the limit that is reasonable? It's a little bit unfortunate that we have to come up with this. Turns out we already have a limit, which corresponds to 16 billion triangles per frame, apparently, worst case. But this limit is not too bad, I think, because, so we have this task work group limit. Let me look at the source code. Do we use this here? We do not. It's used like somewhere else. We have a buffer. So this is where the last time I looked at this code was like a while back. So we have a buffer as 128 megabytes. I forget which one it is. It's probably this one. Yeah. So let's look briefly at the calling code. So we have this code that's generating these task commands. Actually, maybe this is not. This is less bad than I thought it would be because we are already kind of wasteful in memory, maybe. Okay, so we have this WJ limit thing, which is 4 million. The worst case is that we write 4 million task commands. Task command is this guy, which is 20 bytes. So our worst case is that we are writing 80 formula, yeah. So our worst case is 80 megabytes of task command data. Again, this is 16 billion triangles. You probably don't need to render 16 billion triangles, but okay. So maybe that is, but so In fact, I think essentially this means that we have this DCB guy, so this is 128 megabytes. I think instead of 128 megabytes, it could be task glimit resolve mesh task command, which is 20 bytes, and let's just printf this. All right, so yeah, so we have an 80 megabyte task command buffer, and things still work, so hopefully they are still correct. Wait, hold on. Okay. Now the problem is, and this is 4 million tasks that we are submitting. And each task that we are submitting corresponds to a task trade invocation. We can output up to 64 or this guy clusters. So the problem is that we now need a buffer to store like the cluster indices that we are going to render. This buffer needs, by definition, these many entries, and every entry kind of should be 32-bit integer. So it may be possible to pack this better somehow. I was thinking about this last night and I didn't come up with a great alternative. There's like alternatives, but they're not great. For example, you can use smaller bitpack data, but then I think you need a prefix sum operation to actually be able to efficiently access this. I hate prefix sums on GPUs. They are like annoying to write efficiently. I don't want to do it on stream. I don't want to do it off stream. So I think for now we just like store 4 bytes per cluster. Unfortunately, so we have 4 million times 64, which is the worst case amount of clusters that we can render. So this is what, like 256 million times 4 bytes per cluster. This is like 1 gigabyte. Oh man, this is worse than I thought. So like right now, the way this code works is we are relying on the driver to have enough kind of commands in flight, enough task commands in flight, so that even if we do render a ton of triangles, the stages kind of feed each other via the string buffer and stuff, and it all works out. But the problem is that on AMD hardware, like it's actually really slow, right? So that's annoying. I did not know it would be 1 gigabyte before I actually did the math. Did I do the math correctly? I'm assuming I did. Yeah. Now, again, do you need 1 gigabyte? Maybe not. But this is the worst possible scenario, right? And right now we are rendering way fewer triangles and way fewer commands and way fewer clusters and all of this stuff. But essentially we would need to invent a new limit if we wanted to spend less than 1 gigabyte of data on the cluster buffers. And then if the application ever exceeds this number, there's not a great solution to this. Like we can write the code to not like write past the memory limits and stuff like this. For example, if you use more than this number of tasks right now, like you disable level of detail, like you disable something else, you disable, I think right now if you disable level of detail and frustum culling, which I will not do because who knows what this does on this GPU, but essentially you're going to see flickering because the way that the items in this buffer are allocated right now is using atomics, and you're going to see like different items making it or not making it depending on thread scheduling. So that's all not great. I don't have a great solution to this right now, so my solution for now is this. We are going to invent a new limit. Ideally, oh, it even says here 256 million meshlets. So, I mean, I don't want to have space for 256 million meshlets because again, it's like a lot of, it's like 1 gigabyte. We like the number 128 megabytes here. So let's do, yeah, let's say that for now we are comfortable-ish with, and workgroups is the same as meshlets in this case. With cluster indices. Yeah, okay. So that's fine. Now, it's not all this bad because, again, it's like even if you somehow had so many workgroups that you needed this much like space in the task buffers, hopefully you are calling some clusters. Hopefully you're calling many clusters. So practically speaking, this is probably fine, and practically speaking, we probably don't even need this much. I'm not sure. But, you know, the memory cost is unfortunately kind of steep. Like, again, remember, so we are gonna switch to a thing that the driver is kind of managing for us right now, and the default driver size for this right now is around 16 megabytes. It is not working at all well in the driver, which is why we are doing this, but we are kind of spending much more memory now on like compared to what the driver was spending to manage a similar workload. But there's not a great option right now, so. All right. I have these creative variable names, which, you know, hopefully this is not production code, so I'm okay. But we need basically a buffer with like cluster indices. So we'll just call it sib. And then this is going to be cluster limits times 4 storage. Okay. And then we need another buffer. So the way we already did this last stream, we will like have to repeat it now for a different use case, but maybe. Do we? Yeah, because we have to do kind of the same thing. So, but anyway, so like the way we are gonna work is we'll have our compute shader that processes all of these clusters, and then whenever it has visible clusters, it will append them to the buffer. But to append something to the buffer, you need like a way to track the offset in this buffer, and we are doing something similar in the task workflow. So, cluster indices counter buffer, just in case you are wondering what this means. All right, and then we only need this if mesh shading is supported. And then also ideally I would keep the old code somehow, but we are not going to worry about this for now. Okay, so we have two buffers. Now we need a new shader. This is kind of going to do the same thing that our cluster shader is doing, our task shader is doing, but it's going to do it in compute. So for now, I'm just going to copy this shader. We can refactor this later, but for now we basically need, let's call it task call comp GLSO. It's not quite precise, but so we don't need mesh shader here. We are gonna change this in a moment. Man, getting this code to be correct is gonna be painful because this code evolved to be a little bit complicated. Oh, and so the other thing I wanted to note is what IDs are we writing? Because remember, it's a little bit complicated. We have a bunch of meshlets per mesh, and then we have a bunch of instances of each mesh, and like how do we address the clusters individually? What I'm gonna do, I think, is this. Because we already have this pipeline where we submit like bunches of clusters, like tasks, we can use these elements, these like task commands that we have written, and there's at most like 4 million of these or whatever, and every one has up to 64 clusters. And so what we can do is we can just pack the index of this command, which is like 22 bits, with up to 10 bits worth of cluster index inside it, which we don't actually need 10, but it should be like fine, it should be sufficient. We can do like 24 and 8 so that there's room to grow there. It's fine. And that way it should be quick to index the data, because the mesh shader will see this index where it can directly look up the task command, which contains the draw information, some visibility stuff, whatever. And then it can just use the extra 8 bits as like the index in this task. You'd have to watch the previous stream that we did, because it's going to be confusing if you don't know this layout. But that is fine. So there's no payload. Yeah. Do I have the shaders just building? I don't. Why do I not? Oh, have to rerun CMake. Okay. So let's try to get this shader to compile first, and then we'll see. Right, so instead of this payload, which is a special task shader feature that's used for communication, we have to essentially fill these ourselves. And so the way this works, the way this is going to work is that we'll have more buffers. More buffers. Why? Okay. Is there like a write only? Every time I write GLSL, I have to like remember how this language works. So yeah, there's write only. Yeah, so again, we already okay. We already kind of did the thing that I'm doing, just in different kind of instances. Like we have this shader right now that is doing this task command generation that has a buffer of commands and a buffer of counts. And we use atomic add to reserve the space in this buffer and then fill them and stuff like this. And it's the same code that we need, just slightly different, like in spirit or whatever. But okay, so we need uint cluster indices, and then cluster count, cluster indices. I called it cluster index. No, cluster index buffer. Yeah, all good. Okay. And then I guess I called it CICB. Maybe it should just be CCB. Cluster count buffer. All right. And cluster index buffer. Great. Okay. So we are going to submit that separately. There's no payload anymore. And then the way this works is individual threads of the task shader, of the compute shader now, but it's the same thing, are doing calling on individual meshlets. We could append the results individually. In fact, why don't we start with that? Which is going to be bad because it's going to be slower, but that's actually okay. So you know what? Maybe let's just do the right thing. It shouldn't be super hard. All right, so the only difficulty essentially is this. I'd like to write the indices. I'd like to do the minimum amount of global atomics. And the way our task shader code is structured is it's already like doing culling on individual items and then computing the total count of the clusters that have survived the culling. And this is what is used to write all of this to the output buffer, to like the payload. And instead, what we can do is after we have computed this count, we can then write all of this out to like global memory using just a single global atomic. And in fact, if no clusters have survived the culling process, we don't need to touch the global atomic at all, which means that we shouldn't pay the cost that the driver is paying for like 0 elements. It should just be kind of free. All right, so curiously, it's kind of just the payload structure because it's like the same. Oh no, it has right. Okay, never mind. That's fine. So we need task WG size elements, shared count, shared indices, and then if it survived, we don't have payload, but we have shared indices. And then we synchronize, and then we. Oh, but the shared indices are incorrect. So I want to do this packing thing I was talking about, whereas this is already not doing the right thing. Essentially what I want is I want to record the command ID. Why don't I record the draw ID instead? Let me look at the mesh shader. Oh, the draw doesn't have. Yeah, so essentially the problem is in the mesh shader, we need two things. We need the draw index, which is like the instance index, because it has the per instance information such as the number of like the transform and whatever. And also we need the meshlet non-instance index, which is where the geometry is stored. And these are two indices. And it's awkward to partition a 32-bit value into these two distinct pieces, because one is like the total geometry in the scene, like the total geometry data in the scene, and the other one is the number of instances, and they are not really correlated in any meaningful way. And so who knows, like you could select some arbitrary limit. Maybe we should do that. Let me, hold on, because like this is why I didn't do all of this to begin with, because all of this, and you can avoid doing the bit backend by just storing two indices, like the instance index and the geometry meshlet index. But that's, if you just store both as 32-bit ints, then you're now spending 8 bytes per cluster. And I already didn't like the amount of memory we would be using for all of this, so I really want 32-bit packing. But yeah, I think I will just do, this code is going to be annoying to change, but it will need to be changed anyway. I don't even know if I can conditionally. I will need like a separate mesh shader. And I used to use spec constants for this, and I don't know if this would work here. We might need like to play some define games. All right. In fact, I guess we could have played define games here. We'll do refactoring later. For now, we'll just copy code aggressively. Okay. So anyway, yeah. So I think I should probably do. Yeah. Okay. So instead of doing, so we're gonna pack the high the high 8 bits of the cluster index will be the index of the meshlet like within the task, and then the rest will just be command ID. And so it's annoying because the mesh shader will have to repeat this lookup the indirect lookup. But if we don't do this, then we are going to spend twice as much on cluster indices, which I don't want to do either, so it's probably okay. All right, so then we wrote everything to shared memory. We did the barrier. And then what we need to do is we need to copy this. We need to allocate space in the in like the overall command count, I think it was called. Oh, cluster count. So if we have anything to do, and then atomic add has to only be done. This is also annoying. How do we do this? Here? No. Here. AMD should really fix the drivers because I don't like any of this code. How does this work? Oh, here every thread was writing, so we didn't do the aggregation here. Interesting. Interesting. Okay, you know what? This is not the optimal way to do this, but let's actually do the non-optimal thing first. So let's just disable all of this shared count stuff. So we're gonna come back to this, maybe, depending on the performance that we see, but right now we don't even have working code. So like step one, get the code to work. Okay, so then actually we just allocate an index in the cluster count. This is a global atomic, potentially slow global atomic. Not the best way to do this. The driver sometimes optimizes stuff like this behind your back, sometimes it doesn't, like you never know. And then cluster indices, command ID, and then we are done. And then we have this other path in the shader where we don't do culling. And if that is the case, then we just need, is there like a limit on the, yeah, there's task count. So here what we need to do is if this, then we do the same thing, potentially slow atomic, rated, done. Okay, now does this code work? I have no idea. The shader compiles. That's a good first step. The thing we'll do first, though, is instead of just switching like the entire pipeline to this, let's just add this culling thing that I was talking about to our code, and let's just run this side by side with the rest of the code to kind of estimate, like we can actually run the profiler, look at the performance of that individual shader, look at, you know, is it fast, is it slow, stuff like this. So let's just do that first. So and the way this works is all right, so we need to load the shader. Let me check chat. The code editor is Z, Z-E-D. Okay, so I guess we will do, we can just we don't really need this shader if we don't use mesh shading, so all right. I guess we don't even need task submit. Why are we compiling task submit if we don't need to? Oh, I guess it simplifies the code somewhat. Okay, that's fine. Let's do that then. Task submit is something that was added in the last stream, so it's literally like it's been a year and a half and it's basically the same stream except that we are going one level further, which is funny. So create the program, and then we can just run this program. And I have synchronization validation enabled, so we have a bunch of fun barriers to work with, because every time you write Vulkan code, your barriers are wrong. So that is what is going to be the case for us. Let me see. So this is culling, but we don't need here before. Yeah. So. Oh, and there's a difference between late. Oh, yeah, okay. So it's like cull stager, cull shader. So we actually need task cull. Wait. What? Hold on. What? What just happened? Wait, what is task call? Oh, this is confusing. Okay, we picked confusing names before, and now that's coming to bite us. Let's rename this to cluster call. Because we already used the word task call before, and it's gonna be problematic. All right, so here we need cluster call program. And then we need two versions of the pipeline. Wait. Because we have this early pass, late pass, like kind of already covered this. So, and then the way this works is we pass, so we are like using specialization constants that allow us to compile two versions of the shader. Because the work that we need to do is slightly different. And again, the way to think about what we are doing right now is we already had this beautiful pipeline set up with task shaders. And whatever we are doing for task shaders, we now have to replicate in compute to not use the task shaders and instead use the, compute shaders. Is it great? No. But we don't have good options because the other option is patching the driver or ideally changing the hardware, which, Okay, so the shader compiles and the program even gets created, and then we need to destroy it. Let me close this thing now. All right, and now we still have, what did we, oh, right, yeah, we have like buffers that we created that we need to destroy, perhaps. Okay, so we hooked up like the buffers and stuff, but now we have to actually start running the compute shaders. So again, our plan is, instead of running the pipeline where we have task shaders and mesh shaders, we will first run the compute shaders, generates a bunch of cluster indices, and then we are going to render them using a mesh shader, but without using the task shader. And ideally we'd have like it in a separate mode where we can switch between them at runtime or whatever, which is how we did the previous kind of like integration before. But for now, I'm just gonna write it like as is, and then we'll add if statements later. Although, I don't want to complicate that part yet. So we have these cluster call pipelines. which are compute shaders. So we need to bind them, and then we need to run them with basically the same amount of data, more or less. Dispatch. I need to check that the I think it should work. So the beauty about task shaders is that the task shader itself is like a compute shader. So whenever you are invoking a task shader, you can kind of invoke a compute shader instead. You have to rework the connection between the task shader and the mesh shader, which is what we're doing. But in theory, you shouldn't have to rework the task shader itself. So in theory, maybe I should have the if statements here actually, because this is going to be murder to like, it's not even cluster call, it's like cluster buffer. Let's call it cluster submit, and then we'll default this to true. Oh yeah, that's fine. Yeah, I don't want to forget to do some of this stuff later. So let's add a boolean, but for now we're not gonna use the boolean fully correctly because we'll still render like the old way. But we are gonna run the culling shader. All right, so we have the depth pyramid, we have descriptors. We actually don't need all of the data because previously we were running like mesh shaders using the same data. But now we can remove a bunch of stuff. So we do need this, we do need this. Presumably we don't, are we using this? Oh, right, we are doing meshlet culling, so of course we need meshlet data. Right, we can just compact. I see 1, 2, 3, 4, 5, 6. Okay, so we have meshlets, and then we have meshlet visibility. So we don't need data, we don't need vertex data. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Wait, what? Hold on. Commands, draws, meshlet visibility, pyramid. Oh, right, zero based. Okay, 5, 6, 7. Okay. So then cluster indices, and then cluster count. And so again, what happens is we are filling these two buffers. We have the second buffer, which is the counter, and the first buffer, which is the indices. So hold on. Yeah. Okay. Okay. Now, there is two subtleties. The first subtlety is we are using this buffer. We are filling it with the count, but we are also using this as like a global atomic. So it starts at 0 and then increments at 1 for every value that we fill. So we have to clear it to 0. And for that, we have to do a bunch of bearer stuff, which is going to be great. But this is part of why this is all annoying, because like we already kind of did all of this, and now we're going to do this again, but it's fine. Okay. So this is what we need, and we'll probably need some bearer for it. Man, after not having to do deep Vulkan work for a while, all of this is kind of obnoxious, but okay. So we clear the cluster counter buffer, before we do this, we will need some sort of barrier probably. It's probably the same actually because, yeah. And then we will probably need some other barrier after it. Command buffer offset. Command buffer offset. What is the 4 and 1? Interesting. Oh, yeah. 4 is the offset. What is 1 0? Oh, because for mesh tasks it's like a multi-draw, so we are just saying it's like 1. Okay. Well, let's just run this and see if this explodes. Okay. Let's see. Oh god. Okay, right. So all of this work is compute work. So we have to do this before the render pass. So we can't even do an else here. Okay, so that is fine. And then we need this thing is not quite correct. It has to be compute indirect, I guess. It doesn't exist. Dispatch indirect. I guess draw indirect is the same between. Alright. Figuring out the barriers for all of this is going to be great. But okay, so we have a problem. Push constant says overlapping offset 0 and size 112 do not contain. Wait. For each byte, there shouldn't be a push constant. What do we even use push constants for? Globals. Yes. Yeah. Oh, when we compute cluster, when we compile like the shader, we should specify something somewhere. Hold on. Maybe not. Yeah, okay. When we compile the program, we should specify that we are using globals as the data. It's kind of redundant, I'm sure. What do we use it for? Yeah, we like use, it's probably similar to this. Kind of looks similar to this. So we can probably use draw call data instead here. Let me see. It's gonna make it harder to reuse shader code maybe, but if it's easy enough to fix this, then maybe I should. Okay, let's not do this yet. Okay, So the problem with fill, so we have this buffer which we initialize to 0 on every frame, and then we use it to like accumulate cluster indices. The problem with this strategy is that when you have like when you render it for the first time, I think you have to like do a barrier that's like different. This is all annoying. We already did all of this for some other stuff, for like this other counter buffer. So what I should do is I should just check kind of how we work around some of these issues. Oh no, maybe not. Maybe that's not the problem. Hold on. So when we clear it, right after we clear the buffer, we need like a barrier. So we need this. We need a barrier that says we have cleared the buffer, so wait for a clear to finish before starting compute. And also, we have used the cluster index buffer maybe in the previous stage, which we haven't yet, but like we will. All right, so, oh God. All right, pain. All right, so after the fill, we definitely need a barrier. The barriers not on the draw buffers, but like on the cluster buffers. So the counter buffer, we just wrote to using the fill buffer command. And then we are gonna read write to it from a compute shader. The index buffer, we are gonna write to. Before it, we would have used it in the rasterization stage, basically. And this is the other thing we do not need. Okay, so I think this is probably correct. If rasterization stage was a thing. Rasterization stage is definitely gonna be mesh shader, so that's just we can just do this here. There's no variability if we are using cluster culling. We need okay, what the heck is the pyramid? Oh, okay. So let's see, fill. Oh, you guys can see the errors, by the way. Not that you really want to see the errors. Even I don't want to see the errors. Okay, so we had a thing. The issue with sync validation errors, by the way, is that I think there's no useful call stack. So I think if I were to, I think if I were to just run this under GDB, it would show me a call stack that does not actually contain the command. So I have to like infer the command that is being used from like where like what command is kind of failing validation, stuff like this, which can be very painful. Also, ideally, I would have used the debug extension to like annotate objects, so that instead of saying some buffer with an unknown ID, it would say, you know, cluster counter buffer. But that's fine because we are changing code incrementally, so it doesn't really matter. But yeah, so if you look at the call stack, oh no, actually maybe this is not too bad. Hold on. Oh no, never mind. The call stack is showing. Okay, cool. So on this command we have a validation error, Validation error says hazard right after write. We are doing fill buff. Huh? Oh, is it like complaining because it's late pass? Yeah, it's a late pass. So we filled the buffer, then we used compute to render into it. Then we fill the buffer again, but because we aren't using the buffer yet. Okay, so this is annoying because should we disable sync validation? What's the worst thing that could happen? We should. So when I developed a lot of this code, originally sync validation didn't exist. And now there's this trade-off. So there's barriers that I have that will be correct when we finish writing the code, but are not correct right now. For example, right now I'm filling the counter buffer with 0. In the full pipeline, the way it works is you fill the buffer with 0, then you increment it one by one to write the buffer, like indices and whatever. Then you use this counter to render. And then you reuse the buffer again, so then you fill it with 0, etc., etc., etc. So it's kind of like, if you looked at the barrier right now, this is kind of what it's doing. It's saying, oh, hey, we used this for join direct before, and now we need to transfer to it. But the way the code works right now is there's no draw indirect part yet. Like, we aren't using this value yet, with this buffer yet. But it's kind of annoying because it's making it harder for me to develop incrementally. As in, I have to get barriers right as I'm changing the code instead of just getting them right at the end. If I disable sync validation, it will stop complaining, which is great. But I have a risk of crashing the GPU. You know what? If the GPU crashes and the stream crashes with it, so be it. Let's take the risk. All right, hey, the code works. Well, I mean, we don't know. We forgot to destroy some other stuff. Shader module. So I don't know what the order is. Who even knows what the order is? Okay, we're gonna fix the sync validation error later, like, well, that's fine, who cares? Let's try to run this under the profiler and just see. So, Mesaviki cap Mesaviki trace frame, is that, I guess this is right. So we don't have, we could like run this code under render doc. And inspect the data in render doc. I don't know what render doc will say to our messed up barriers right now, so I'm not sure that's a good idea, but maybe that's a good idea. But let's just look at the trace first. So again, what we are doing right now is we are incrementally changing this code. We still have all of the code that we are running, that we ran before, but in addition, we have code that in theory should do culling and then output a buffer with cluster indices to render, where an index packs like the index of the task that the cluster came from with the actual index of the thing. In a sense, we have the task shader and mesh shader, and they're connected by this payload. And what we are doing is we are just saving this payload to memory, running for all of the tasks that we want to render, and then we will like render from that buffer. So because we haven't annotated anything, it's going to be hard to like know. But we only have a single dispatch indirect. And in theory, this is our dispatch indirect. And we should be running it twice, once to produce cluster indices for the second pass, and once to produce cluster indices for the first pass. And if we go here, somewhere, wait, how do you scroll this thing back? Okay. Is this, yeah. So we run it twice. It runs very quickly, which is suspicious. But in theory, this is essentially like, is our code correct? Who knows at this point? Like we have a shader runs, the shader produces some data. We could run under RenderDoc. I don't even have RenderDoc downloaded right now, so I don't want to do this. Which I can easily download RenderDoc and stuff like this. It's not a problem. I just am not sure. I'm really worried of crashing the stream, and I don't know how RenderDoc will behave on potentially invalid barrier code. Maybe it's fine. So, but ostensibly what is happening right now is that we are generating this buffer with a bunch of cluster data to render with a counter. And then we're just not rendering from this data. We're not rendering from this counter. There's two things that could go wrong. One is the counter could be super large. So as in we are like running the code that probably fills these buffers. We might not be filling them with the right information. If we use this information, the GPU might crash. It might crash if the counter is too large for some reason. Oh, we don't have, by the way, which we actually should do. Let me add a to-do, which is like not optional. Actually, I don't need a to-do. So if we run out of this buffer that we like pre-allocated to be kind of large enough, but like hopefully large enough, then bad things may happen. So we are gonna fix this here. There's another problem, which is if we are generating too much data with this, if we are not gonna write commands past the buffer, but the count of these commands will be too large. But this is not an issue because we need to do a transformation like which we already had a shader for, which might just work. Oh, this buffer doesn't clamp. Well, it clamps. All right. We need the same thing now. Okay, that's fine. Yeah, so the problem that we have yet to solve, we could just like run a drawing direct now, right? And maybe we'll have to change the mesh shader a little bit, but like maybe it magically works, and if it magically works, you know, victory, except for like code cleanup and stuff. But the one thing that prevents us from just doing that is as follows. When you So we have accumulated a bunch of cluster data, which, you know, maybe this code is correct, maybe this code isn't correct. We can check if this code is correct or not by inspecting this, either in RenderDoc or not. But regardless of this, though, the one thing that we have yet to do is to transform. We are filling this buffer, we are ending up with a value that is the number of clusters that we have written. Let's say this number is like 1 million clusters, whatever, right? Then we need to do an indirect draw that will use mesh shaders to actually render all of these clusters. And we want one mesh shader per one value. So it seems simple. What could possibly go wrong? Well, the problem is when you do an indirect dispatch, an indirect like mesh submit or whatever, you're telling it not a number of mesh work groups that you want, but a three-dimensional grid, X, Y, and Z, because all of the dispatches and all of the APIs, except for NVIDIA Mesh Shader, which we're not using, is three-dimensional. This is annoying for two reasons. One is, I mean, it's a three-dimensional grid instead of like a one number, so that's like it just you have to do some extra work. But the other one is the x dimension of this grid has limits. The limits are somewhere here. Let's try to nope. Let's so I don't remember where they are, but oh yeah, okay, these are the limits. So we can output up to 64K mesh shader. Wait, there is a total limit of 4 million anyway. Oh my god. Jesus Christ. Oh my god. This is this realization where your entire plan like doesn't work because the API is stupid. All right. Cool. And we were like circumventing this limit before. How did this work? That's stupid. Hold on. Yeah, because it reports the same limits. Oh, it actually says task or group can be up to 1024. Okay, that's fine. Oh, huh. That's actually very interesting. This limit might not be fully correct. I'm not sure. It's a little suspicious. Why would there be a 4 million limit on the mesh invocations or task invocations? Huh. Well, if this limit is real, working around this is going to be so painful that I'm not going to do it this stream anyway. So let's just ignore this problem, this specific sub-problem of the total set of problems that we are dealing with. All right, but anyway, the point is when you're submitting dispatch of mesh workgroups, you have this 3D grid. The 3D grid is 64K by 64K by 64K max, or rather like the limit on every dimension is like 64K, and then the total limit is 4 million, which I'm now not sure if it's true, and if it's true, we need to split into draw calls, and splitting into draw calls is insanity. So maybe this whole AMD thing is just completely busted, and we should just, you know, sell an AMD GPU and plug my 4090 back. But maybe the numbers are just broken. It's fine. The more pressing issue is this. If we have more than 64K clusters, we just can't submit them in like a one-dimensional dispatch, because the limit on every axis is 64K. So we have to split it into like a 2D or 3D grid, and we already have code that does this because we already have ran into this problem when we were using task shaders, because they have the same restrictions spiritually. And if this is true, this is just broken, because 4 million times like whatever 100 triangles is like 400 million triangles in a single draw call if you are not using task shaders. This just can't be right. This just can't be right. All right. Anyway, so we have to run the code that takes us from 1D into 3D, and we already have written this for task shaders, and we need the same thing for mesh shaders. Why is there a can we just run this shader? No, because when you do this, let's say you have a 1D buffer that's like 15 items, and you want to split into a 4x4 grid. 4x4 is 16. Now you have one extra item. And we have this code that pads stuff. I guess we could have done this differently. All right. You know what? Let's just write the code. So let's call this cluster submit. We need another shader that is going to do kind of the same thing. It's going to take commands, etc. But instead of doing command count, it's going to be cluster count. So we take this 1D value, that's the total number of clusters that we have written, and we split it into groups, or like into grid. And the only reason why this code is doing extra stuff is because it's filling the extra items that are a natural kind of byproduct of doing this kind of split with zeros. We don't even have a zero value, actually, now that I think about this. Because like, there's no cluster ID that you can like not draw. So the only way for this to actually work is for the mesh shader to actually compare with like the real count, which is annoying because it's not actually too annoying. Everything is complicated. Do not write graphics code. It's bad for you. Okay. You know what? Whatever. So submit. Ideally, I should merge these back. Like, so I know how to rework this code to be nicer, but I'm already like halfway into, you know, rewriting everything. And so I don't want to be like even more into rewriting everything. So what I should do first is I first should get things to work with like in like a weird state where like maybe, you know, betas aren't working or whatever, like things are weird but working. And then from a weird but working state, it's easier to get to not weird but working. So this is just weird. So there's like a 4 million. I still can't believe this. This is so broken. This is so broken. All right, this is so broken. So we can't even reach the 32 million per the spec. Do we need more than 4 million right now to 56? I think we don't. Okay, temporarily. Temporarily. How am I gonna submit this with all of this to-do crap? I guess I'll have to do this boolean. I'll have to keep this boolean, but like default it to false and then like figure out how to rework this later. Okay. So count, and then actually use cluster limit, and then there's no reasonable zero value though. Should we just append 0 for now and deal with it later? Yeah, because like what has to happen is ideally we essentially submit a mesh shader work group that like renders no geometry. But mesh shader has all of this beautiful code that like accesses a bunch of data. So there's not like a way to correctly do this. This is all broken. Does this have access to... No. The correct way to address this is to like pass this buffer to the shader so that the shader can also clamp. Oh! Okay. This is not great, but we'll just write like all once, and then in the mesh shader, at least we don't have to read this extra weird buffer. Okay, that's fine. Okay, so we have to have a second shader, which is kind of like task submit, but cluster submit. And this shader is going to be the shader that fixes up our 1D grid into a 3D grid. So that's great. This is like questioning your life choices. Okay, so fortunately, at least the shader is straightforward, and then we have a bunch of stuff to destroy. Right. Fantastic. So now, whenever we submit the thing, if you want more context for all of this annoying stuff that we are doing right now, then it's similar to the previous stream, because in the previous stream we had to do the exact same thing where we have a counter buffer, we clear it to 0, we like allocate some stuff, but then we have to split it into like a 3D grid. So the split has to happen basically here. So we just rendered the counter, and then we take the counter. Yeah, this is all correct. We take the cluster counter buffer that we just filled, and then we like patch it in place so that instead of a 1D thing, it also has a 3D information in it. We do this with the cluster submit pipeline. It's a 1-by-1 dispatch. Why do we need the DC? Oh, cause okay, we actually don't. Oh no, sorry, we are using this, right? We are padding the index buffer stuff with it. Oh god, hopefully this works. Oh. Well. All right, you can tell my mental kind of processing resource is exhausted, so I don't even know what to call this. Let it be descriptors too. All right, so maybe right now we have filled the counter buffer with a 3D grid, and the index buffer with like a non-3D grid. And maybe this buffer is correct and we can render from it, or maybe not. There's two ways to find out. One is we can like run render doc and stuff, and the other one is we can just try. Oh man, it's been like 2.5 hours almost, so I kind of want to just try, and then if the GPU crashes and burns, so be it. Because but we need like a new shader for it anyway. Let's just copy the shader and just freaking do it, and if it doesn't work, it doesn't work, and you know, it's fine. We'll call this cluster.mesh.glsl, and it's gonna be a mesh shader without a task shader. So there's not gonna be a payload. Obviously, all of this duplication of the code is like not good, and the way to fix it is by like either using the preprocessor or the spec constants. I'm just not sure if the spec constants are valid here, because like there's a payload that you need for task shader and not for. So I'm not sure if specialization constants can be used in this case. All right. And then instead of this payload, what we have is we have these global buffers that we have already used here. And we also have the count. We don't need the count because we have this trick. Okay. I think maybe this will work out. Maybe our code has bugs. And if it does, then it will not work. But maybe our code does not have bugs. And then things will be great. Which one is it? We do not know. So we need cluster indices. And that's it. And then instead of payload meshlet indices, yeah, so we need this computation basically. But instead of so this is like CI cluster index, and then CI is split into the task to get data from and the like cluster, the meshlet index within this task. So we need to decompose it back. Oh my god, if this works, it's gonna be a miracle, people, because I'm kind of doing this semi-blind. So task commands CI, and this is the task. Oh, the draw. Because we don't have the payload anymore. But then, wait, where is the? Oh, this was MI. And then to get the, wait. All right, hold on. I suspect that this is like impossible to follow at this point, but you know, that is fine. So somewhere here we should have the correct computation, this one. Yeah, I think it should be just command task offset plus this local, no, this one. All right, does this work? I have no idea. Does the shader compile? No. Oh, read only. Okay. All right, we are close to be able to try to run this and see what happens. This is insanity. The stream is still live. People are checked out. There's 36 people watching me like suffering and writing code that probably doesn't work. Thank you for your emotional support. All right. The big reason, so there's this limit of 4 million that I'm not even sure if that limit is real. Like, this approach is gonna have to be even more complicated to be fully generic. But like also the problem is, I strongly suspect that on NVIDIA, what we are doing right now is counterproductive. Not in the sense of you don't need it, but in the sense of you do this and your code becomes slower. Cool. But on AMD, like, you do need it. So reconciling these is not fun. And like the fact that you have to rewrite a bunch of infrastructure to like remove a task shader is also not fun. It's kind of necessary, but you know, it's unfortunate that this has to happen. Anyway. All right, enough complaining. More working. So there's no task shader anymore. We need like a second mesh shader. And then we are gonna use that second mesh shader without a stat. At least the fragment shader is like, if I had to rewrite a fragment shader, I would just be, well, it's simple, but still. Mesh program, and then cluster program. Wait. Okay. Okay. I think that's fine. Oh, and the other reason why I want to keep the task shader code in is like, I'm really hoping AMD can improve their drivers. And if they can't, I'm hoping that RDNA 4 or 5 or 6 or something, like at some point, you know, hopefully the hardware is just great for this use case. And once it is, we don't need all of this code. So, but clearly in the current driver state, we do need this code. So that sucks. All right. So we have compiled the shaders. Maybe the compilation fails. Wait, silently? How is that possible? Huh. Whoa. What? So like it can't link. What? Whoa. That is funky. Oh, Thank God for assertions. Okay. The pipeline linked, and then we have to destroy a bunch of stuff. All right. So okay, we have pipelines that have compiled and linked. Should we just try to render with them and just YOLO and see what happens, or no? Yes, thank you for emotional support. For people in Europe, so usually these go for a couple hours, and it's already been 2.5. For people in Europe, it must be getting late. But I want to get this code to the point where it runs, and then we actually see that performance is good. And if we do, then, you know, we like duplicated a bunch of shaders, and like we can deduplicate it back with like if devs, it's just like busy work, it's fine, you don't even have to do it on stream. And there is this 4 million question that's bugging me. There's zero good solutions to the 4 million question, because I don't trust AMD's command processor even to do multi-draw. And so if the 4 million is a real limit, I guess you can like split in the same submit shader that we duplicated. You don't have to split into, okay, so if we run into the 4 million limit for real, actually we can fix it. Okay. So my concern right now is essentially, let's say I change the code to use these buffers that we have been filling. If the code doesn't work, then the GPU explodes or whatever, which is going to be unfortunate. The big issue is the stream will die. Do we need the permit? We don't, right? Was the pyramid previously in like 5 and 6 and stuff? Yeah, this we don't need, or rather it like migrated. Wait, did it migrate? Yeah, okay, cool. So yeah, okay. So then after vertex data, we just have cluster indices and that's it. Oh, this is the Meshlets visibility buffer. Yeah, so we just need this to do double check synchronization. No, we are not double checking synchronization. All right. This code needs like refactoring, but okay. We still need the task commands, but we need the no. Yeah, okay. The offset is still 4. The draw call count is still 1 and 0. Is this the draw call count? Oops, sorry. Draw count and stride, yeah, okay. So this is the code. Do we just run it and see what happens? I'm worried, because if there's like a bug in the code, then anything may happen. You know what? YOLO. Oh my god, the code worked first try, and it's render late is a little slow for, I'm not sure why that is. But the overall frame time is good. This is interesting. Render late is like slower than I would have expected, and early is faster than I would have expected. That is counterintuitive. Huh. The code works. The code works, people. We need an RGB capture. Let me disable occlusion culling and hope nothing explodes. Oh, also hold on, 31 million triangles, it should be 17. I think what happens is the render late pass is like redoing the render thing. How is that possible? Maybe we are doing when we are doing cluster calling, we are not like correctly doing occlusion somehow, because it looks as if we are redoing the same draw call like twice. So somewhere in the second pass, we are like using code from the first pass. Something like this is happening, which it should not be. But I'm not sure what that is. I mean, we also still do this slow atomic thing, but this cannot be the problem. This cannot be the reason why we have more triangles than we should. So what should happen is that in the second pass, we just don't render anything. We still do culling. Let's do RGB capture. Oh my god, I'm happy that the stream didn't explode and, you know, stuff like that. But somewhere there's a typo or something like this, because my expectations, well, my actual expectation was that the GPU would have hung. But since it didn't happen and we're actually rendering the oh man, this is so nice. Yeah, okay. So there is some bug. So if you look at the occupancy and stuff, the early pass is actually great. So we have one draw call, And again, just so that people have some idea as to what's happening. There's like a bunch of draw calls, and then every draw call requires us to draw a bunch of meshlets. We just concatenated like all of this into one giant buffer with cluster indices. The way the indices are packed allows us to go back into various buffers and pull in all of the information to actually synthesize the geometry. But from the API perspective, there's like one draw call. This one draw call is like a very large draw call, and it's using meshlets instead of triangles. So if you look at the parameters here, I'm not sure if it will show them actually because it's indirect. It might not. But like we are submitting 200,000 wavefronts for primitive shader, which is this meshlet shader equivalent in hardware. Or maybe, oh, this is the sum. I see, okay, yeah. So we are rendering essentially 200,000 clusters in the first pass. One cluster is approximately 96 triangles, but it can be smaller for low LODs. So it's somewhere in the neighborhood of 22 million triangles. It should be 17 million. So this kind of adds up. But then whenever every mesh shader work group runs, it can pull in all of the geometry it reconstructs. So that's cool. That all works. I'm shocked that it works, but like, hey, the numbers actually add up. And if you remember the previous traces, we can actually look at some of them. This is the terrible one. This is a new one. This is this the old one? I guess I haven't saved the 32K context one, Q1, whatever. But even the best case scenario that we had, which I closed the file, but what we had here is during the rendering, we were utilizing the geometry pipe, which is this green thing, fairly well for like 10% or whatever of the duration, and then it kind of dropped off. So the bottlenecks were still there, we just didn't like see them clearly. And now, if you look here, this stage is working well. It's like the same utilization of geometry. Now, should green be higher or not? That's a mesh shader problem that we can explore separately. And what we pay for this is a bunch of memory, of course, and then also the culling thing before it, which is this. Like it's not full. One of this is a clear, but it's like roughly this. It's like 20 microseconds of work. Right, because it doesn't do occlusion culling. Yeah, in the first pass. Yeah. So like the cost is actually fairly small in the time from the time perspective. But what should happen in the second pass is that we run the culling and then produce zero work, because remember all of our expectations, all of the clusters are like visible consistently, and this should only draw clusters that should be visible but haven't been visible past frame. But this doesn't happen for some reason. And we still dispatched, yeah, oh, the pixel wavefront is small. Wait, what? What? Hold on, what? Interesting. So it submits a bunch of work, but little geometry. That is confusing. Oh, but I guess geometry would be depth tested. Never mind. Yeah, okay. So there must be a bug somewhere where in the second pass, we either run like the wrong shader pipeline or something, or like we run the right shader pipeline, but like the culling doesn't work, like something like this. Something bad is happening. Oh, the beautiful thing at least is actually late is unused. Okay, this is not the reason for why we have a bug, but we don't need this late thingy because we don't actually use specialization constants. So that at least we can delete, and that makes our code slightly cleaner. Oh, let me disable. Okay. But yeah, okay, so, all right, I'm feeling optimistic. Wait, but then we don't need, what is the mesh? No, mesh, yeah, okay, never mind, all good. Yeah, let's see. So when we compile cluster call pipelines, we compile them with the specialization flag. Constant ID is 0, so that's correct. And then there's supposed to be a bunch of weird code here that, like, you know, has conditionals and stuff, but I'm assuming it works because it's the same code that the cluster shader was running. But essentially what should happen in the second pass is that this code shouldn't execute much or at all after the first frame, because this thing should tell it, hey, we like have rendered the thing already in the first pass, so don't touch it. But like something around this code isn't working, and I don't know why yet. So we build a pipeline from the shader, from the program, etc. So that's, oh, but then we never use it. Ha ha ha. Wait. No, we do use it. Why? Hold on. What? No. Okay, never mind. Hold on. We do use it. This is interesting. Our barriers are messed up, by the way, obviously, because, like, you know, we haven't re-enabled validation. But usually when barriers are messed up, you would see like flickering or something. Like, it would be rare. Well, in theory, it is possible that a missing barrier could lead to this odd behavior. It's super unlikely. Nah, it's basically, I'm gonna call it impossible in practice. But we should fix the barriers. Like, the fact that the barriers are likely incorrect right now is a problem. It's just that something else must be causing. This is interesting. So, like, how is this? We might need render doc for this. The debit buffer is correct. So collision culling, like, is working, and well, maybe. The number of triangles is about double of what it should be. If I disable a collision culling, whoa, 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 huh. Okay, so the problem isn't actually with cluster occlusion. The problem is with the draw culling or something. How is this possible? So without cluster occlusion enabled, we still kind of render essentially double the geometry. And we broke the regular. Wait, how did we break that? What the heck? Oh, it's because it's set to true. Hold on. Cluster submit mesh shading supported. All right. No, what? Oh, no. It's the same. Right. Okay, sorry. So for now, I guess this should be the same. Ideally, I should rework stuff a little bit. All right. So there's like cleanup that should happen. Yeah. So there should be 53 million triangles. If smaller, there should be less than 53 million. I think it was 47 or something like this. But if in our new mode we get 95, so we're definitely just rendering everything twice, even when cluster occlusion culling is disabled. So this means this should be impossible. Did we like clear? This is so weird. This should definitely not happen. What if I disable occlusion culling completely? It's still double. Okay, the bug is very stupid, because this is not like a complex condition somewhere. This is like something just very stupid is happening. I'm just not sure why. Did I change some code like accidentally without meaning to? because we are like almost done. Like everything almost works, except for barriers and like runtime switching. But because this is just confusing. What should happen? So we have a bug even if we disable occlusion calling. What should happen when you disable occlusion calling is that the draw call list, that calling that we are doing, is producing 0 draw calls. So like, where are we getting the draw calls? That is so weird. What the heck? Dispatch indirect, draw call count buffer 4. This is the offsetting thing. I am confused. We might need render doc to figure out. Even with render doc, actually, it might be difficult to figure out because. But the bug must be very stupid. Like, this cannot be a complex bug. Did we change shaders somehow? We don't even have diffs in the shaders because all of the shaders are new. That is insane. Where is the bug? What is this? No, yeah, that is correct. Pipeline. Interesting. Weird. Task submit is set to true, which we should. There is an opportunity to refactor a lot of this, but to refactor code, you should fix the code first. I think we might need render doc. Now, this sucks because like we're almost at 3 hours, and if this code worked, especially if the barriers worked, I would just like ended the stream and then we can do follow up on like cleanup or whatever. We can do like a refactoring stream, but this code doesn't work. So I can't even like submit this code. It's like it's like slightly too broken. Why? So weird. Okay. Cluster call. So it's as if cluster calling dispatches with the old draw count. How? Oh my god. Wow. I expected bugs, but I did not expect bugs that are this weird. Task call late. Yeah, that's all correct. So weird. Maybe I keep clusters. So the weird. So here's the problem. Like the buffers are reused, but so the way this works is this. First, you have the stage that generates sort of draw calls, or in our case, it's like slightly smaller granularity than meshes because of the things I was explaining earlier. So that does generate that generates commands and the command count. And then before we started reworking all of this, we would just submit a task shader indirect thing that used these commands and command count. And then this whole process is repeated twice, early and late. And the buffers are reused. So it's of course possible that we are reusing the count. My problem is like we didn't change that code. What we changed is that after this code runs, we now have another stage that kind of takes the count and stuff like this. And so I just don't understand how it's possible that the count, I mean, I guess we need render doc. Essentially, if the count is wrong, it should have been always wrong. Which, I mean, is that the assumption? That would have been funny, because that might change. It might change a lot of stuff. But like, it just feels like essentially if this were the problem would have been noticed sooner, because this part of the part of the code that would have been broken way before, like before the last stream, before, like, because like a lot of this code dates back. Oh, and right. The other thing is when we disable, what happens when we disable the mesh pipeline again? Yeah, when we disable the mesh pipeline, the outer thing that like renders objects into stages, that's like the same code with the minor tweak of, it just blows my mind. We need like render doc. So like there is a little bit of a difference between the code that runs in these cases, but it's literally like isolated to either you fill a command per draw call and use traditional rasterization pipeline, or you split these draw commands into like groups and then fill them, fill more than one potentially. But the visibility logic, like filtering logic, all of this shouldn't be affected. Maybe that's wrong. I think we need render doc though. Oops. Because I just don't see the bug. It's just mind-blowing how this bug can happen. I don't understand this. Let me just double check. So essentially what I'm claiming is that there is this buffer DCCB. Maybe I'm just not using it right. What I'm claiming is that in the second pass, this buffer should have been 0 all the time after the first frame, unless you enable cluster occlusion culling. Because this is just how the code works, like if you don't need to call clusters, then your second pass doesn't do work. So the fact that the code is displaying double the triangle count, even when I disable, oh, is there, hold on, let me disable this here, just to see that I'm not crazy. Yeah, okay, yeah. So, we can actually validate this theory, by the way, because even without render doc, we can like migrate this buffer to CPU and then just read the contents on the CPU, and we will know what the second pass rendered with. But what I'm claiming is essentially this buffer should be 0. I should have 0 commands in the second pass, unless we enable like cluster occlusion culling. But our bug exists regardless, so it can't be that. Maybe it's the barriers. It just would be crazy for this to be the barriers. But maybe it's the barriers. Okay. But let me check that it's used correctly. So we fill it, and then we convert it to like a 3D layout. So now it has the 3D layout. And then we do like barriers and stuff. Yeah, and this is the buffer that we use in the cluster submit. We zero out this buffer. Maybe this code is misbehaving, because if the counter of clusters is misbehaving, then even if the calling stage produces no work. So maybe that's the problem actually. That I could buy. So let's say this counter fill just isn't working for some reason. Like, I don't know, something weird is happening. This fill doesn't work. And instead of being zeroed out, it kind of retains the previous contents. It's unlikely, but I could buy that. Like, I wouldn't be super shocked if this is what's happening. I would be just shocked. So then the theory is this code, but it's like a subtle bug, because like the code kind of works. It's just that for some reason the second pass doesn't like. So maybe it's the bearer, because if this is the bearer, it would be the weirdest bearer bug I've ever had, because usually the way bearer bugs work is different. It's not like, oh, you have consistently wrong results where the right just gets like swallowed. It's like, no, stuff is flickering and like it's sometimes wrong, sometimes right. It never looks like this. And this is wild. This is wild. This is wild. Let's do the thing I was saying we can do, which is we'll migrate these buffers to host. No, not this buffer, sorry. So we'll migrate this buffer and then the second counter buffer, this buffer. I think the code should still work. Yeah, so now after the after we finished rendering the frame, we already like synchronized with the GPU and stuff. So what we can do is we can essentially print draw counter buffer, and it should be 3 ints dccb data, and then of course it's not like this. I guess we can do this. Wait. And then cluster counter buffer. And then this is only the data from the second pass, because again, we are reusing both buffers. We are doing call, call, draw, call, call, draw. But the second pass is the one that's broken, so you know, that's like convenient in our favor. What the heck? What? What? Wait, what? What the hell? These numbers are correct. These are what I would have expected for the correct operation of the code. So when you disable cluster occlusion culling, which is the current state, the draw counter buffer is 0. So why there are four values? The first value is the thing that we atomically increment on. And so this is like the counter that's used. This is the linear number. And then the last 3 are this 3-degree transformation that we do. So when we have 0, instead of 0, we do 0 times 64, right? Which should be equivalent to nothing being like rendered. But anyway, so if we have cluster culling disabled, then both numbers are 0. The draw call stage generates no commands. Then the cluster stage generates no commands because there's no draws to like generate them from. and then nothing should be rendered. So it's mind-boggling as to why I'm just freaking lost. It would be hilarious if this is like, well, maybe bearers trigger some weird, like maybe dispatching direct is like weird in some way, because I've never used dispatching direct until like this moment. But why is it no problem? Anyway, confusing. When cluster culling is enabled, this is actually the correct state, because as I was saying earlier, you do have to process the draw calls the second time. Previously, we would do this in the task shader. Now we do this in the separate compute cluster culling stage. The reason is you have to compute and update the occlusion culling status to make sure that if anything should be drawn, you are drawing it. And if you don't do this second pass, like there's no way for you to kind of reconcile that. But you expect that as an output of this, nothing will be actually visible, no geometry will be submitted. So what the heck? One thing I want to check is actually maybe the totals. No, that can't be right. All right. Triangle count. I want to render separately the triangle counts that we have. Oh, maybe it is the bearers. That will be hilarious. Huh. Interesting. Okay, maybe this is the bearers. This would be wild. I would have to like think about what exact implementation of the driver leads to a bug manifesting in this way when the bearers are broken. But the thing that makes me think it might be the bearers is the count in the first pass is stable. The count in the second pass, it's not. But the scene is completely static. There shouldn't be a reason for it. Because again, the expectation is all of the clusters have consistent visibility. So everything that has ever been visible in this configuration is rendered in the first pass, and the second pass renders nothing. But the fact that we have like some number of triangles rendered in the second pass, and it's not actually the same number, we are not rendering 17 million. So that makes me think maybe it's the bearers. It is confusing that when you disable stuff, like how do zero draws generate like 47 million triangles? All right, I think we need to fix the bearers, and then hopefully that fixes our problem. I'm not looking forward to this because bearers are obnoxious and bearer errors are obnoxious, and just in general, I'm not looking forward to this. But okay. We need to do this under GDB so that we at least have the stacks. Oof. Nothing is stopping me from launching in RenderDoc. I just need to download it. But the CPU debugger would not help. I mean, like we wouldn't have to add a print, but like it's actually faster to add a print. Yeah, I mean, maybe we should just use the RenderDoc, and maybe it's just faster. Oh, wasn't there's like a rad thing. Hold on. So there's like a rad thing that should trigger like aggressive barriers on behalf of the app. It still might be the rad debug sync shaders. Let me try this. Oh, right. Oh, no. Wait. Don't leave me. Okay, hold on. It was the barriers. Oh my god, people. See, this is the issue with using RenderDoc for stuff like this. Even if I'm not sure what the result would have been, but it sounds like the lack of correct barriers in our case is preventing something to be like, it's something like this maybe. For example, let's say that there's some issue with updating this counter before the command processor actually, this is actually super likely. Oh my God, this is of course what's happening. Yeah, that explains everything. So I think what's happening is this: we don't have we knew we don't have barriers, but the crucial barrier that I think we don't have is like the barrier that waits for the for the compute shader to finish before kicking off the indirect draw that comes after it. What happens in this case is that the command processor is free to look at this buffer like before the compute shader actually finishes writing it. In which case it's actually likely that it will more or less consistently see a wrong result. The value that we are printing at the end is like different because that's like, oh, compute shader is definitely done. If you run under RenderDoc, there's a risk that RenderDoc will insert more aggressive barriers between commands because it would need to like capture the output of these commands. And there's a risk that the bug disappears under RenderDoc. So there's a risk that under RenderDoc we run this scene, and I don't want to do this because again, like I don't have RenderDoc installed, and it's just been like 3 hours at this point. But there's a risk that RenderDoc just doesn't show this bug. Okay, all right. Rad saves the day because this would be a good time to tell people who don't know this yet. Recent AMD drivers have this thing called like AMD experiments or something like this, AMD driver experiments. They might have a similar setup where they aggressively insert barriers between just like every command. And if they do, this is like useful to diagnose this. So now we know that we don't just need to fix the barriers to make sure that we don't have theoretical issues. Now we know that our practical issues that happen are because we don't have barriers. All right. So now we have to fix barriers. That sucks. I hate fixing barriers. Let's undo the print stuff we did, which we don't need because we know what the problem is. Well, at least we know what a problem is. This is actually great. So this means that once we fix the barriers, our code will work correctly. And then we have all of these limits and code duplication and whatnot that we're gonna like solve some other time. Let me actually first try to strategically add a barrier. Oh, and by the way, all of this stuff is like, you can't see this on the screen, doesn't change, we just render too much stuff. But the time frame changes, so this render late pass should be way faster, and the triangle count should not be 31 million, it should be around 17. So I think the crucial barrier that we are missing, and we are gonna fix all of them, hopefully, but the crucial one that we are missing, oh, maybe we'll fix one of them, and then actually commit this, and then we'll fix, anyway. The most important one that we are missing should be between the compute shader and the indirect dispatch that happens after. It should be literally after this thing. So after we do the dispatch that transforms the 1D grid into the 3D grid, I think I probably up until this point we are fine, maybe not. But we are doing compute to compute barriers and stuff like this, like it's probably fine. I'm not 100% sure, but it's probably fine. But then what we have to do is we have to wait for compute to finish doing this until drawing direct starts. So we already have a barrier like this, so we can just copy this. It should be like, no, not this thing. It would be hilarious if we don't have, no, this is the correct one. Yeah. So the most important one that we need is this one. After cluster counter buffer is written with this 3D grid information, we need to wait until that is finished before we launch drawing direct. We have a secondary problem with the cluster index buffer. It's less severe because it's like, yeah, these two barriers are kind of the same in a sense, but like it would be correct to do a barrier on both, where before the mesh shader starts reading the indices of clusters to read, we also need to finish the compute writes to this resource. In practice, I believe the driver will likely just merge these, because it's like, not merge this rather, like this barrier is probably stronger in practice, but there's cases where this barrier can also result in some commands being written to like clear the caches in between. This is the issue with barriers, is like if you don't have a barrier, you can have behavior anywhere from your code works correctly, happens to work correctly, to the thing we have, which is somehow consistently the code has stale data. But there's also an in-between state where randomly some reads return correct values and some return stale values, and you just don't know what's happening. So it can be like a variety of, yeah, 17 million. All right, so our code is working correctly now. I'm sure sync validation is still complaining because we don't have all of the barriers. We just have all of the barriers that we happen to need here to demonstrate victory. And the timings look really good. This is faster, I believe. This is how the code should have always performed, essentially. Everything here is way faster versus the task shader code we used to have. I will have to plug the task shader code back in to demonstrate this. Let me just do this now, because at this point, you know, what's a few extra booleans to plug in? So when you press T, we are gonna alternate between using task shaders and not using task shaders. We're gonna also write the state in this thing that's very long now. Let's just do it here. That basically you should not like wait, oh I see, right. So it's like if mesh shading is enabled, then yeah, okay. And then the task submit name is kind of unfortunate now, because like, oof. So I think this is kind of how it should be. I think things should work okay with the setup. Yeah, cool. So, and then if we press T, we have great performance. This is amazing. Yeah, so I unfortunately undid the method changes that allowed us to run. I'm not going to redo them, but I believe that essentially even we started all of this because in the cluster culling configuration that you really want to actually gain full advantage of the meshlets, because that allows you like to cull way more geometry than you could otherwise. We started all of this because the second pass was just catastrophically bad. Like it should have been almost instant, and instead it like wasn't. But it helps even if none of these things are used. Essentially, like you're at the point where on AMD hardware, just if you have task shaders enabled, it's like a bug. It's like a performance bug because it feels like it's just like never fast. But which is to say, even without this catastrophic problem, the use of the task shaders in the first stage was still significantly limiting our performance. And now with that bottleneck lifted, for example, let me press the appropriate buttons. So right now I have task shaders disabled, so we have the code that we have been writing on stream running. But occlusion culling of clusters is disabled. So the cluster culling is like there, but it's not as efficient because there's not as much stuff to call. And now we're running at 3.37 for the entire frame. And if I go back to the traditional rasterization pipeline, we are running 10% slower, like 3.65 or whatever. This is how it should always, this is how it like should have been for forever. But until we did all of this work, like it just wasn't, because the task shader, like using it at all would hamper our efficiency. And then of course, once we enable cluster occlusion culling, then our frame time is 1.44 milliseconds, which is way lower. I think with the RAD patch, I think I had like 2 milliseconds frame time total. And the render late pass in particular was still 0.4 or whatever, 0.34. And I think I said at the time, I'm not sure if this is right, I'm not sure if it should be faster, but it's hard to know. Now we know. Like it shouldn't be. Like it's actually super quick to do occlusion culling for whatever number of clusters we generate. It's just the CPU bottleneck is like bad. Anyway, AMD, please fix this. This is not sustainable. Let's do an RGB trace. Oh, no, sorry. Wait, hold on. I need to go back to like. So people, remember how I told you that what could happen is we crash things? Well, we did crash things, so that is great. The stream should be back fully now, right? Yes. The recovery process was pretty quick. Hey, so what happened is, what happened is I enabled RGB tracing and it crashed, but the barriers are broken, so maybe that's why, who knows. I'm not going to use RGB again. I wanted to profile this to demonstrate the beautiful capture. Yeah. But what happened instead was that the driver crashed, or I guess the GPU hung. What would happen on Windows in this case is that the specific application that generated problematic workload would die, but the system itself would recover after like a second. What happened here is the system was stable, but the entire graphics interface crashed, and that kills every single program that runs, including OBS, which terminates the streaming, which, you know. But hey, the good news is we are back. I don't have any programs running, so that's fun. But okay, so where I was going with all of this is able to have good performance on AMD hardware. Is in theory we should have beautiful fast rendering now. The stream crashed. Hopefully it doesn't crash again. Okay. So the stream crashed when I tried to capture another performance trace. I assume maybe that's because I'm using the code that has broken barriers, and so that I could believe can create problems. So let's just fix barriers. Oh my god, this is a really long stream now, but okay, that's fine. Let's just, we started this, let's just freaking finish this. Wait, what? Hold on, that should be impossible. So I fixed one barrier, right? Like the one that I knew that was bad. Is there no other barrier that is necessary? That is just suspicious. Huh. State of disbelief. There's two problems. The first problem is I thought we'd have more barriers to fix. It's just unlikely that there was one barrier that was breaking our behavior. I knew where it was after thinking about why this problem can happen. I fixed it without checking sync_val. And now sync_val has no errors. The validation is enabled for sure. That is suspicious. And then, of course, the second problem is the GPU just died when RGP was enabled, which is suggestive of some sort of issue that is still there. But maybe that issue is not because of the barriers, but because of something else. Yeah. Anyway, you know what? I would have loved to end the stream by showing the RGP trace of good code, of code that's working well. But like if I run RGP again, it will probably die again. I can try to run this code on Windows on RGP, but that's like a machine reboot and stuff like this. So I think it's been 3 hours and 25 minutes. I think we should just wrap this up. So I think the way we're gonna wrap this up is as follows. Let me, should I keep this as true? Should I keep this as false? There's like some stuff to fix. I think the limits, like if we render more clusters than we have space for, I'm not confident that the code is correct. Also, in theory, we should probably fix this slow global atomic thing. It seems to be fast enough in practice, so maybe that doesn't matter. But because of the RGP crash, I'm just not confident this code is, you know what, it's fine. This code is like not production code, so it's probably fine to actually commit it as is. So I think what we'll do is we'll just commit this code, and then we'll end the stream. And then the remainder of the work here in theory is what? So refactoring. We have had to duplicate like a bunch of shader code essentially in a way that is not nice. In a way where if we have to change one of them, we'll have to change another one. So that should be fixed, but unfortunately that requires some preprocessor like stuff. We can't use specialization constants for this essentially. And then there's still some lingering bug maybe, because the RGP crashes the GPU with this code enabled. I actually don't even know in what configuration it ran. I would have to like debug the RGB problem essentially. And every time I hit it, the stream will crash. So like I shouldn't do it on stream. And that's kind of it. It would be nice to profile this code on NVIDIA, to profile the two modes, to understand like what's better, what's worse, etc. But that's a problem for another day. So let's submit what we have. I think we are in a good spot. We have written code, the code works, the code is fast, the code might crash your GPU, but you know, it's close enough. So I'm just scanning, and yeah, I'm just suspicious of the barriers. Maybe I shouldn't be. Let me think. The interior barriers should be fine. This one is correct and symmetric. Maybe I'm like unreasonably suspicious of the barriers, because I can't point to a barrier that is missing. I'm just surprised that the only missing one was the one that broke everything. Maybe that's what it is. And then like ideally there's some other refactoring on this code that's necessary anyway, but this could be done some other time. It's fine. So, and then we have, of course, a bunch of shaders in, yeah. All right. So, day 21, heroically implement cluster culling ourselves. And because of MDCP bottleneck that we are hitting again, but this time in the task shader emulation, async compute work that driver is submitting is stalling the geometry work in render early and is just heavily bottlenecked by the serial CP processing in render late. This is significantly affecting the performance of Meshlet culling pipeline in all configurations, even ones where cluster occlusion is disabled. Fixing this requires us to run task calling, like cluster calling, and compute this task ourselves. Fill a cluster index buffer 4 byte per visible cluster overhead, and use mesh shaders without task shaders. On 7900 GRE, this is dramatically speeding up our pipeline. So I think it was like 10 milliseconds to 1.4 milliseconds with cluster culling enabled, and then like 5 milliseconds to, what was it, 3.21 millisecond with cluster culling disabled. Let's double check these numbers and then get out of here. This is task shader enabled because I have the boolean flipped. This is a disabled 3.4. Okay, fine. 3.4, and then 1.4, and then actually disable this. Alright people, I think we are done for today. Thank you everyone for watching the stream. We did crash the stream when we were already done, which was funny. I will debug the RGP problem offline. I don't know, it can be caused by a variety of factors. It could be the caches are stale, so the problem doesn't even exist. It could be that the problem is real and we're missing barriers. It could be that we are hitting this freaking 4 million limit somehow, because the first time you render, I just don't buy it. 4 million is 400 million. There's no way we are hitting the 4 million limit. Must be something else. So maybe RGP has a bug, maybe not, who knows. I will need to double check on Windows and stuff like this. There's some code refactoring that needs to happen here. I might do this on stream, I might not do this on stream. The reason why I do this streams is it's like less, I don't think I think better on stream than I do offline, but I think this process is educational, but also the first hour of the stream was explaining like a very general problem, and to understand this problem you need to know kind of like if you understood the first hour of the stream, then you have a really good grasp of how modern GPUs work. And so that's fantastic, right? The refactoring of the code that has yet to happen is like kind of mechanical, so I'm not sure if I'll do this on stream, we'll see. But either way, the stream recording will be live on YouTube. I will update the repository with a link to it. Thank you everyone for being there. Small kittens in the far are actually flickering. Oh, this was before we fixed. Yeah, I think this was this barrier where it rendered. Anyway, like there's hopefully it doesn't happen anymore. Let's just double check. think that's fine. I should say there's some, there's a funny thing where I have a frustum that is using an artificial far plane for culling that is not present in the projection matrix to not render objects that are far away. When you enable cluster culling, what happens is clusters like are called by this far plane that would have been visible before. So essentially what I'm saying is when you switch some modes in the viewer, sometimes the picture doesn't change, but sometimes it does change, which ideally wouldn't happen, but it's kind of, it's fine. But yeah, I think our synchronization issues are gone now. It's just RGB that's the problem. Anyway, oh, right. And this is, by the way, the problem that we were having was the problem turning on validation layers or turning on synchronization validations would have basically shown us the problem. The reason why I didn't do this is because I was worried that there's like 5 barriers that we need to fix. And even if one of them fixes the problem, it would take forever to like place all of them correctly. It turned out there's only one barrier we needed to fix, which is odd. Anyway, capture with experimental resting barriers is actually what fixed or what found the problem for us. So that was super good. And yeah, I think we are done. Thank you everyone for attending. I do not know if there will be more Niagara streams, but if there will be, then, you know, Twitter, Mastodon, blah, 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 you know where to find me. All right. Done.